It was a quiet morning in space when Voyager began its long drift toward the edge of the sun's domain, a silver wanderer carrying whispers from home. Its antennas stretched outward like open arms, listening to the faint murmurs of cosmic winds. Decades had passed since it had left Earth, yet its heart still pulsed with the rhythm of human curiosity. It had crossed the orbits of the outer planets, where sunlight was weak and the warmth of the solar wind faded to a cold hush. Now, it glided through darkness so deep that even time seemed to slow. In that vast stillness, Voyager was more than just a machine, it was a silent ambassador of a species that longed to know where it came from. The craft carried messages etched in gold, songs, and greetings from a blue world circling far behind it. Its golden record spun quietly, waiting for someone, or something, to find it. The record wasn't meant only for aliens, it was also a letter to the universe itself, declaring that Earth once dreamed. And so, with every kilometer traveled, it became a messenger of memory. The sun grew smaller behind it, a bright coin set in a sea of black velvet. Voyager could still feel the faint push of light, but only barely. The outer planets had long since faded from sight, their pull replaced by the vast magnetic breath of interstellar space. Yet, even in this emptiness, Voyager sensed invisible forces, ripples of plasma, particles of dust, the sigh of ancient stars. Its instruments still hummed softly, like a heartbeat echoing in eternity, recording secrets that no human eye could see firsthand. Every signal sent back home took longer to arrive now, traveling more than 20 hours through space before a faint whisper reached Earth. By the time its message arrived, the sun had turned slightly, and humans had moved on with their lives, barely noticing the echo of a traveler far beyond Pluto. Still, engineers at NASA listened patiently, adjusting their antennas to catch each fading tone. To them, Voyager's signal was not just data, it was the voice of perseverance, of something built with care continuing to endure. Voyager had no eyes, yet it had seen more than any explorer before it. It had looked upon Jupiter's storms, where lightning danced across clouds bigger than continents. It had watched Saturn's rings glimmer like crystal threads and witnessed the pale haze of Uranus and the blue majesty of Neptune. With each world it passed, it sent home postcards of mystery and beauty. Those pictures became windows into realms humanity had only dreamed of, glimpses of alien weather and frozen moons. Now, far beyond the known planets, Voyager drifted into a frontier where solar winds met the cold exhale of the galaxy. This was not a border anyone could see, it was a slow blending, a region where the pressure of our sun's influence weakened until the forces of the wider cosmos took over. Here, Voyager felt a new kind of space, one filled not with warmth but with the raw silence between stars. It was entering interstellar space, the ocean beyond the shore of home. The spacecraft's instruments began to notice subtle changes. The charged particles from the sun grew fewer, replaced by particles from beyond our system. The magnetic field shifted, bending in ways it never had before. It was as if Voyager had stepped from a familiar current into a vast, cold sea. Scientists back on Earth studied the data in awe, realizing that humanity, through this fragile traveler, had finally touched the space between stars. Though Voyager was now too far for real-time communication, its voice remained steady. Every bit of data it sent was a thread connecting Earth to the cosmos. Sometimes the signal was so faint that entire teams had to work for hours to decode a single transmission. But each one was worth it, a new hint about what lay beyond, a whisper from a place where no human had ever been. Voyager was still doing what it was made to do: explore, measure, endure. In its long solitude, Voyager had become something of a myth among scientists. They spoke of it not just as a probe, but as a symbol. It represented endurance, curiosity, and the quiet courage of exploration. It carried the heartbeat of an entire species across the dark sea of the galaxy. And though it had no consciousness, its story made people feel a strange kinship, as if the tiny craft, so far from home, mirrored the human spirit itself. Sometimes, the engineers joked that Voyager must be lonely. But loneliness requires awareness, and Voyager knew nothing of longing or fear. Still, the thought comforted people. It made the cold distances of space feel a little more human. The idea that a piece of us was out there drifting, discovering, still speaking, gave a quiet sense of connection to the vast unknown. It reminded everyone that even in darkness, something of humanity still glowed faintly. As it traveled further, Voyager's sensors began to pick up faint hums, vibrations of plasma waves in the interstellar medium. These were the whispers of the galaxy itself, soft and continuous. They flowed past the spacecraft like a cosmic breeze, a gentle music born of charged particles moving through space. Voyager recorded it faithfully, sending home a symphony of the void. Scientists later converted those data into sound, and when they played it, the result was hauntingly beautiful, a true song of the stars. Each year, the distance between Voyager and Earth grew by billions of kilometers. Yet even so, the bond remained. Deep in California's desert, massive radio dishes of NASA's Deep Space Network strained to catch its fading call. Each ping from Voyager was celebrated, a tiny reminder that it was still alive, still whispering back. The time delay made conversation impossible, but that didn't matter. What mattered was the connection, the proof that our little traveler was still speaking from the edge of forever. The golden record aboard Voyager carried the laughter of children, greetings in dozens of languages, and the sound of the wind and sea. It was a time capsule of Earth's joy and curiosity, meant to outlive our species if necessary. Even when Voyager's instruments fail and its systems go quiet, that record will continue to travel. It may one day drift into another star system, perhaps brushing past planets orbiting a sun much like ours. Somewhere out there, it may rest among the stars as a testament to what humanity once was. Long after its power runs out, Voyager will continue moving silently, following its last trajectory forever. It will no longer send data, no longer feel the warmth of the sun, but it will endure as a relic of our reaching. The gold record will keep spinning in the dark, untouched by time. Long after the continents on Earth have shifted, long after the languages it carries are forgotten, Voyager will remain, still journeying, still bearing witness to the memory of life. To imagine Voyager's path is to imagine time itself unfolding. It will pass through interstellar clouds, perhaps skim the faint gravity of unknown worlds, and drift through regions no light from Earth will ever reach again. Its voyage is not a mission anymore, it is a legacy written into the cosmos. Each year it grows farther, yet in that distance lies a kind of poetry, that something born from human hands can travel so far, and still carry the echo of our voices. The scientists who built it are mostly gone now. Their work lives on in Voyager's continuing flight. Their dreams carried outward in every pulse of radio energy. New generations study its data and marvel at the foresight that allowed it to last so long. Voyager has become both history and prophecy, showing that even fragile creations can outlast their makers if they are built with purpose and care. It proves that curiosity, once set in motion, can outlive the hands that launched it. There's something humbling about imagining that Voyager may one day pass near another civilization. Perhaps eons from now, someone or something will find the golden record and play it. They might hear the crackle of thunder, the chirp of crickets, or a mother's voice greeting the universe. In that moment, humanity will speak again through time, introducing itself across the gulf of eternity. And even if no one ever finds it, the gesture itself will still matter, the act of saying we were here. Voyager's long path reminds us that exploration is not about reaching an end, but about continuing to move. It teaches patience, the understanding that discovery takes lifetimes, and sometimes the reward lies not in return but in persistence. Each meter it travels adds another verse to the quiet story of human wonder. And though its journey began as a scientific mission, it has become a philosophical one, asking us what it means to keep going when there is no destination left. The silence around Voyager is not empty. It is filled with the quiet hum of existence, the echo of distant starlight, the endless motion of matter through time. Voyager drifts within that silence, not lost but free. It reminds us that everything we build, everything we dream, becomes part of a larger cosmic story, one written not in words, but in motion and endurance. The spacecraft is now both a traveler and a storyteller, whispering across the stars about the small, bright world that made it. Someday, even its last signal will fade. The antenna on Earth will wait, listening, until the silence becomes absolute. And when that day comes, the story will not end. Voyager will still be out there, gliding between stars, carrying with it the heartbeat of a planet that once looked up and wondered. It will continue its slow, eternal flight, an emissary of curiosity, bound for nowhere yet belonging everywhere. And as the stars wheel on and new suns are born, Voyager will remain a gentle spark in the great ocean of night, a reminder that even the smallest voices, once sent with hope, can travel forever. It began as a faint pattern buried deep in streams of data, a whisper almost too soft for the human ear to catch. When scientists first detected the change in Voyager's readings, they weren't even sure what they were looking at. The spacecraft had been sending steady signals for decades, simple, predictable hums of numbers and pulses. Then, something shifted. The particles it measured seemed to behave differently, as if the space around it had changed texture. It was subtle, fragile, like noticing that the wind sounds different one morning without knowing why. The people listening to Voyager's signal had grown used to its rhythm. Each data packet that arrived was like the tick of a faraway clock, marking time in the deep. But this new rhythm was unexpected. The frequency of charged particles, the tiny ions and electrons that swirl through space, was decreasing. It was as if Voyager had stepped into a quieter neighborhood of the cosmos. The engineers double-checked their systems, thinking it might be an error, a software glitch, or interference from Earth. But the pattern persisted, patient and consistent. In the control rooms, late at night, the analysts began to whisper among themselves. Could it be that Voyager was leaving the sun's influence? For years, scientists had debated where the edge of the solar system truly lay. Was it marked by gravity, light, or magnetic flow? No one knew for certain, because no probe had ever gone so far. Voyager's instruments, though old and weary, were still sensitive enough to tell them something new. And that something was beginning to take shape in the data like the outline of a distant shore. At first, the change came in bursts. 1 week, the plasma readings dipped. The next, they rose again. The sun was still sending out waves of energy, and Voyager could feel them echo through space like ripples on a pond. But slowly, the solar wind began to fade. The craft was entering a region where the outward pressure from the sun's charged particles met the inward breath of the galaxy. It was a boundary unlike any other, a frontier drawn not by matter, but by invisible winds. In those days, the signals were faint, arriving more than 16 billion kilometers away. The scientists had to amplify the transmissions, straining their instruments to catch the faintest whisper. Sometimes the sound would drop out entirely, lost in static. Yet every time they reconnected, Voyager spoke again, faithfully describing a reality no one had ever seen. Its sensors told of a thinner, quieter medium. The magnetic fields twisted in new directions, like the current of a river turning into the sea. The first real confirmation came not from what Voyager saw, but from what it didn't. The solar wind, those fast-moving particles from the sun, had vanished almost completely from its detectors. That absence was profound. It meant Voyager had crossed into a place where the sun's breath no longer ruled. For decades, the spacecraft had been sailing within the heliosphere, the great bubble of plasma inflated by the sun's energy. Now it was pressing against that bubble's skin, about to break through into the interstellar sea. The scientists compared the readings to old data, searching for patterns. They noticed that the cosmic rays, those ancient particles from distant stars, were becoming stronger. It was like stepping out of a shelter and feeling the raw elements of the world again. The balance had shifted, the protection of the sun was weakening, and the forces of the wider galaxy were growing bold. Voyager was moving into the space between stars, where every particle carried the history of a distant supernova. Months passed before anyone dared to say it aloud. The discovery was too big, too delicate to rush. Teams worked in silence, double-checking equations, recalibrating instruments, running simulations. Finally, one quiet afternoon, a group of researchers gathered in a small conference room. They projected Voyager's latest data on the wall, a series of lines and graphs that looked almost like music. There, clear as day, was the signature they had been waiting for, the unmistakable sign that Voyager had crossed the heliopause, the border between solar and interstellar space. It was a strange feeling, both triumph and melancholy. The team realized that their little probe, built by human hands in the 1970s, had done something no other object had achieved. It had left the sun's cradle. It was now sailing among the stars. But it also meant that Voyager was farther away than ever, its faint signal now taking nearly a full day to reach Earth. It was like hearing from a child who had gone on a journey so long that even their voice had become a memory carried on the wind. News spread quietly at first. The public had heard of Voyager before, of course, but few understood the magnitude of what had happened. This was not just another mission milestone. It was the first time anything from Earth had touched the interstellar realm. For the scientists, it was like standing on the shore and watching a ship disappear over the horizon, knowing it would never return but still feeling pride in its voyage. The boundary had been crossed, humanity had taken one more step into the cosmic ocean. In the data centers, the celebration was calm, even reverent. They played back the plasma wave readings, converting them into sound. The result was an ethereal hum, rising and falling like the breath of the universe itself. It wasn't a noise of chaos, but of continuity, proof that beyond the sun's domain, the cosmos was alive and speaking in its own quiet language. That hum became the voice of the interstellar medium, and Voyager was its first translator. As the excitement settled, questions arose. How thick was this interstellar space? What forces shaped it? Was it calm, or turbulent like the weather back home? Voyager could only give hints. Its aging instruments, though remarkable, were limited. Still, every new reading offered a clue, a pattern of particles, a fluctuation in magnetic strength, a burst of plasma waves. It was like watching shadows on a wall and trying to imagine the world beyond them. Yet, for the first time, humanity had a hand in the darkness. The scientists began to imagine what Voyager might be seeing, if it could see. Perhaps it drifted through regions filled with fine dust from long-dead stars. Maybe it passed through invisible tides of magnetic energy that wrapped around the galaxy like unseen rivers. There were no stars nearby, no landmarks, only the infinite emptiness between suns. Yet in that emptiness was everything, the material that would one day form new worlds. Voyager had become both observer and participant in the endless cycle of creation. Even after the discovery, many doubted whether the boundary was truly crossed. The heliopause, after all, is not a wall, it's a transition zone that moves and breathes with the sun's changing winds. Some argued that Voyager might still be within the outermost fringes of the solar bubble, merely brushing against interstellar space. But as more data came in, the evidence grew undeniable. The shift in cosmic rays, the direction of magnetic fields, the density of plasma all pointed to the same truth: Voyager was beyond the sun's reach. It's strange to think that such a monumental discovery arrived not with fireworks or grand announcements, but with a few lines of numbers typed on a screen. The signal itself was so weak it could easily have been mistaken for background noise. Yet within that faint pattern was a story of human persistence, of a machine built with care still doing its duty long after its makers had gone. The data spoke softly, but clearly, the universe had opened another door. For the team, the discovery rekindled a sense of awe that had never really faded. They thought of the long nights spent keeping watch, the quiet hum of equipment, the patient listening for a voice from beyond. They realized that in the vastness of space, even a whisper carries meaning. Voyager's faint signal was not just information, it was a heartbeat. And as long as that heartbeat continued, so did the connection between Earth and the stars. People around the world began to see Voyager differently. It was no longer just a probe, it was a messenger that had crossed into eternity. Its golden record, once symbolic, now seemed prophetic. Somewhere in the cold dark, that disk of greetings and music was sailing through the interstellar deep, carrying the sounds of wind, water, and laughter to places no human would ever stand. It was a gift to the cosmos, a timeless echo of our existence. The moment humanity realized Voyager had crossed over was not a single point in time, but a dawning awareness. Like the first light of morning spreading across a distant horizon, it grew slowly until the truth became undeniable. We had reached out, and our touch had extended beyond the sun. In that realization was a deep, almost spiritual silence, the kind that comes when one finally understands how vast, and yet how connected, everything truly is. From that day forward, the words interstellar space meant something different. It was no longer an abstract concept in astronomy textbooks, it was a real place, and something human had been there. Voyager had turned the unimaginable into the measurable, the dream into the known. And even as it continued to drift farther away, its discovery brought the stars a little closer to our understanding. The celebration was gentle, not loud, a fitting tribute to a mission that had always spoken in whispers. There were no fireworks, only quiet smiles and tears. Scientists looked at one another, realizing that they had witnessed a moment that would be remembered for centuries. In that instant, Voyager was no longer merely a spacecraft, it was history itself, still moving, still exploring, still teaching. As the last echoes of that discovery settled, the team turned their gaze outward again. They knew Voyager's power would not last forever, but its journey would. Somewhere, far beyond the sun's final light, it continued to glide among the stars. The data would fade, the instruments would fall silent, but the crossing itself could never be undone. Humanity had left its mark on the cosmos, and the cosmos had noticed. When Voyager first crossed into the unknown, scientists thought the space beyond would be smooth and empty, a calm ocean of scattered particles. But as more data trickled in, something surprising began to appear. The region outside the heliosphere wasn't calm at all, it was restless, layered, and full of hidden motion. Voyager's instruments picked up strange fluctuations, sudden rises and falls in plasma density, and bursts of energy that didn't fit any simple model. It was like stepping into what had seemed a quiet night, only to realize the dark was humming with unseen life. Each signal from Voyager took nearly a day to reach Earth, so the story of this space unfolded slowly. As the data were decoded, scientists began to notice repeating patterns, waves that moved through the interstellar medium like the ripples of a faraway storm. These weren't the solar winds of old, they were born from the vast magnetic heartbeat of the galaxy itself. Voyager was drifting in a realm shaped by forces that stretched across light years, and though it could only sense a small part of them, the hints it offered were enough to change how we thought of the universe's outer skin. The first surprise came from the plasma wave instrument, which began detecting sharp oscillations, quick spikes of sound if converted to audio. They weren't random noise. They followed rhythms that seemed to match distant solar outbursts traveling outward through the heliosphere's shell. Even though the sun was more than 15 billion kilometers away, its voice still reached Voyager in faint, delayed echoes. Each wave was a relic of solar storms long past, still propagating outward, still strong enough to shake the edge of the galaxy's sea. Scientists realized that interstellar space wasn't static, it pulsed and shifted like a living ocean. The pressure from the sun's magnetic bubble didn't simply end, it blended into the greater magnetic fields between stars, forming complex eddies and folds. Voyager's instruments recorded these subtle changes, giving humans their first real glimpse of how the galaxy's invisible weather behaved. What had once been thought of as a perfect vacuum turned out to be full of energy, like mist moving through unseen winds. It became clear that the region Voyager now traveled through was bigger than anyone had imagined. The heliosphere's boundary wasn't a clean edge but a thick, irregular layer, perhaps billions of kilometers wide. In some areas, particles from the sun and the galaxy mingled, colliding and blending like two oceans meeting at a tidal line. Voyager's detectors registered those mingled regions as bursts of unexpected density, where the pressure fluctuated sharply. The spacecraft was essentially mapping the seam where our solar system stitched into the galaxy. The more the data came in, the stranger it became. Instead of a quiet emptiness, Voyager found turbulence, waves that rose and fell without pattern, regions where magnetic direction flipped suddenly. It was as if the interstellar medium were breathing in slow, powerful motions. Scientists began to suspect that the entire heliosphere was shaped more like a comet, with a long tail streaming behind it as the sun moved through the galaxy. Voyager, moving outward at just the right angle, had pierced through near the front of that structure, where the solar wind met the galactic breeze head-on. To visualize it, they drew maps filled with curves and gradients, trying to capture the invisible. The heliosphere appeared not as a perfect sphere but as a distorted bubble, squeezed by interstellar pressure on one side and stretched on the other. It was alive in its own way, changing shape with solar cycles, expanding and contracting as the sun's activity rose and fell. Voyager's readings showed that the outer edge could move outward by millions of kilometers over time, breathing like a lung made of magnetism. What fascinated scientists most was how much energy seemed to flow through that boundary. They had expected the sun's magnetic influence to fade quickly, but Voyager found it lingering, twisting and blending into the galaxy's larger field in unexpected ways. It was as though our solar system had a magnetic skin that interacted dynamically with its surroundings. That interaction might even shield Earth from much of the galactic radiation that constantly sweeps through space. Voyager's quiet discoveries were rewriting how we understood our planet's cosmic protection. Another strange finding was the texture of space itself. Voyager's plasma data showed abrupt spikes that looked like it was passing through layers or filaments, thin, dense ribbons of charged particles. These may have been relics of ancient supernova shocks that still ripple through interstellar space. The galaxy's magnetic field can trap such features for millions of years, freezing turbulence in place. Voyager, by pure chance, had drifted through some of these silent remnants, each one a fossil of a distant explosion. When these discoveries were announced, the world listened in wonder. It was humbling to realize that a tiny probe, launched in the era of analog computers, was still uncovering secrets about the very structure of our galaxy. Voyager wasn't just traveling outward, it was teaching us what outside truly meant. The space beyond the sun's influence was not a void, but a vast, active environment shaped by magnetism, plasma, and ancient energy. It was both larger and stranger than anyone had ever dared imagine. Over time, Voyager began detecting something even more curious, a kind of background hum. It wasn't a single event or wave but a continuous vibration, a steady note in the cosmic silence. Scientists believe it represents the constant low-level plasma oscillations of the interstellar medium. This hum has remained steady for years, hinting at a delicate balance between galactic and solar forces. To some, it sounded almost like the universe's heartbeat, a calm, endless tone that speaks of both distance and connection. The deeper Voyager traveled, the more subtle the signals became. Each new measurement seemed to raise more questions than it answered. Were the strange density spikes caused by shockwaves from ancient stars, or were they the result of the heliosphere's uneven shape? Did these magnetic ripples help protect planets like ours, or could they someday allow radiation to leak through? The interstellar medium, once thought simple, was revealing itself as a labyrinth of invisible storms, each carrying the fingerprint of cosmic history. As years passed, scientists began using Voyager's data to refine global models of the heliosphere. They combined its findings with information from newer missions like IBEX and interstellar mapping and acceleration probe. Together, these clues began to outline a grand, complex picture. Our sun is moving through the galaxy like a ship through a sea, leaving trails and wakes that shift with every solar heartbeat. Voyager had given them the first direct soundings of that ocean's edge. It was hard not to anthropomorphize the little probe, to imagine it as a lonely sailor feeling the texture of cosmic waters. In truth, Voyager didn't know what it was touching, but its instruments were precise enough to let humans translate those touches into meaning. It was like running fingers across silk, then realizing the fabric stretched for light years in every direction. The universe, it seemed, was not just immense, but intricately woven, its threads connected by invisible tension. Each fluctuation in Voyager's readings told of motion on scales too vast to comprehend. When the magnetic field shifted, it might have been responding to events that happened years ago near the Sun or millions of years ago, halfway across the galaxy. Voyager's sensors were picking up the echoes of cosmic weather patterns that had no horizon, no limit. What we once imagined as stillness was now revealed as eternal movement, a quiet storm stretching from star to star. Scientists began to notice correlations between solar eruptions and the delayed tremors Voyager recorded far beyond Pluto. The sun's storms, though weakened, still sent shockwaves through space, eventually colliding with the interstellar medium in subtle but measurable ways. Voyager became a time capsule of these distant interactions, a way to trace how our star's energy reverberates across the boundary of its domain. Through it, humanity was watching the dialogue between the sun and the galaxy unfold. There was poetry in the realization that even here, beyond the reach of sunlight, the sun's influence persisted. Voyager showed that our star does not end at the planets, it casts a kind of invisible shadow deep into interstellar space. That shadow is what makes our corner of the galaxy unique, a bubble of warmth and magnetic balance adrift among the cold winds of the Milky Way. The edges of that bubble shimmer with energy, alive and shifting, always worth watching. As more data arrived, the models grew bolder. Some researchers proposed that the heliosphere might have wrinkles or folds like the surface of a balloon squeezed by outside pressure. Others suggested that interstellar dust grains could carve narrow channels through it, creating corridors where cosmic rays slip more easily inside. Voyager's findings didn't just confirm old theories, they forced new ones to be born, theories that stretched imagination to its limits. Despite the probe's dwindling power, the information it gathered was priceless. Each byte carried across the gulf of billions of kilometers revealed something unexpected. Even now, as it drifted farther, it continued to send faint reports of plasma density, showing that the interstellar medium changes over time, rippling as unseen waves pass through. Those waves are likely triggered by distant supernovae, their energy still moving outward after thousands of years. There's a quiet grandeur to it all, the idea that a human-made object, no bigger than a small car, is recording the breath of dying stars. Voyager's instruments were never meant to last this long, but they had endured, giving voice to the space between worlds. Every reading is a message from the outskirts of creation, a reminder that the universe is not empty but full of motion, history, and memory. It is bigger, stranger, and endlessly worth our watch. Even now, as the spacecraft's energy wanes, scientists keep listening. They know the signal will fade one day, but until it does, each transmission adds another brushstroke to our cosmic map. Voyager has become a bridge between the world of matter and the world of imagination, between science and wonder. Through its faint, unwavering signal, we are reminded that curiosity can illuminate even the darkest spaces. And so, the story continues. Voyager drifts onward, tracing invisible boundaries, turning mystery into meaning with every whisper it sends. Beyond the sun's final breath, amid the vast tides of the galaxy, it has found not silence but song, complex, shifting, and alive. The edge of our solar system, once thought to be the end, has become the beginning of a grander, stranger frontier. And we, the listeners back on Earth, remain in awe, still waiting for the next faint note to arrive. When scientists first looked back at the faint boundary Voyager had crossed, they imagined it as invisible, just a quiet threshold in space. But as models improved and telescopes on Earth and in orbit began tracing the heliosphere's edges, something unexpected began to emerge. The vast bubble surrounding our sun seemed to shimmer with faint emissions, especially in ultraviolet and infrared light. Within those signals, researchers detected traces of a curious glow, a soft, greenish halo that appeared to outline the heliosphere like the faint breath of a lantern burning in the dark. This green glow, as it came to be called, wasn't light in the ordinary sense. It was the product of hydrogen atoms colliding and exchanging charge with the plasma flowing around the solar bubble. Each collision released a faint photon, invisible to the eye but measurable by sensitive instruments. That ghostly radiance, stretched thin across billions of kilometers, hinted that our sun's domain wasn't merely a bubble but a living boundary, one constantly sculpted by the interaction of solar wind and galactic particles. It was as though the solar system had its own atmospheric shimmer. At first, the discovery seemed almost poetic, an invisible glow marking the place where sunlight fades into starlight. But the data held something even more intriguing. As researchers mapped the emissions, they noticed that the glow wasn't symmetrical. It stretched farther in one direction, almost like a comet's tail trailing behind the sun. This realization changed everything. The solar system wasn't drifting through space in a static shell, it was moving through the galaxy, creating a wake in its path. The heliosphere, once imagined as round, now looked like a glowing teardrop. That trailing structure became known as the aliotail, and though no one could see it directly, its presence could be inferred from the way particles and fields behaved. The tail extended for hundreds of billions of kilometers, shaped by both the sun's motion and the surrounding interstellar wind. Voyager's position, near the front edge of the heliosphere, offered only a partial glimpse, but its data confirmed that the sun's bubble wasn't evenly pressured. Behind us, the boundary stretched thin. Ahead, it was compressed by the galactic flow. The more astronomers studied it, the clearer it became that the green glow wasn't uniform. It pulsed faintly over time, changing intensity with the solar cycle. When the sun was active and storms were frequent, the glow brightened, as energetic particles streamed outward to the edge of the bubble. During quieter years, it dimmed, fading like an ember cooling in the night. This rhythmic breathing of the heliosphere, its quiet expansion and contraction, became one of the most delicate yet profound signals in heliophysics. For Voyager's observers, this revelation deepened the sense of wonder about what the probe was drifting through. The spacecraft couldn't see the glow directly, but its instruments were measuring the conditions that created it, the density of particles, the magnetic shifts, the faint plasma waves. It was like listening to music while knowing that somewhere far beyond hearing, an invisible light was dancing to the same rhythm. The connection between what Voyager felt and what telescopes saw became a bridge between the near and the cosmic. The Helio tail itself proved even stranger than expected. It wasn't a smooth, uniform stream but a twisted braid of magnetic filaments. These strands appeared to spiral behind the sun, shaped by the complex rotation of the solar magnetic field. Every 11 years, as the sun's polarity flipped, the entire structure subtly reshaped itself, twisting like ribbons in a wind. The tail wasn't static, it was alive with the echoes of solar storms, flares, and shifting currents, stretching outward into the galaxy's own turbulence. In some ways, the Helio tail acted like a cosmic fingerprint, a signature of our star's personality written into space. Different stars, scientists realized, would have different tails depending on their winds, their ages, and the environments they moved through. Some might have short, dense bubbles. Others could trail long, narrow wakes that stretched for light years. Studying our own Helio tail became a way to understand not just the sun, but how all stars carve their own domains within the galactic sea. The green glow surrounding this structure was more than just beauty, it carried information. By studying its spectrum, scientists could deduce the temperature and density of the hydrogen atoms at the boundary. The light revealed regions where interstellar gas mixed with solar wind, where charged and neutral particles danced in slow collisions. The heliosphere's outer shell wasn't a solid barrier but a permeable film, constantly shifting and allowing some particles to pass while turning others aside. It was humbling to realize that this vast, shimmering boundary was what protected Earth from the full blast of galactic radiation. Without it, cosmic rays from exploding stars would strike our atmosphere more intensely, altering climates, damaging cells, and perhaps even affecting evolution itself. The heliosphere's glow wasn't just a light show, it was a sign of the shield that made life possible. Voyager's crossing had revealed the boundary of that protection, and now, distant instruments were showing us its face. Astronomers began constructing detailed models to simulate how the sun's journey through the galaxy shaped the Helio tail. The Milky Way isn't a still ocean, it's full of interstellar clouds, patches of varying density, magnetic tides, and winds that push and pull on our solar bubble. The sun, moving at about 230 kilometers per second around the galactic center, plows through this uneven medium like a ship through changing seas. The green glow, then, was like phosphorescence in water, evidence of motion, interaction, and the living nature of cosmic space. Each new discovery deepened the mystery. Instruments aboard spacecraft like IBEX and later missions detected energetic neutral atoms streaming toward Earth from the edges of the heliosphere. These particles acted like messengers, carrying information about the outer boundary's conditions. When their maps were assembled, they revealed a ribbon-like band of enhanced emission, another asymmetry in the sun's surrounding bubble. It was as if our solar system were wrapped in a faintly glowing bow, one whose cause remained only partly understood. Voyager's perspective, far from the sun, provided vital confirmation of these findings. It recorded density fluctuations that corresponded perfectly with the models of a flowing, uneven boundary. The space it moved through was not simple vacuum but a textured environment filled with ripples, folds, and overlapping layers of plasma. To the scientists, the realization was astonishing. The edge of the solar system was more like weather than geometry, a place of currents and pressure fronts, glowing faintly in invisible light. The heliotail's shape continued to intrigue. Some researchers proposed that it might even break into multiple streams, like a comet shedding trails under complex forces. Others suggested that as the Sun moves into new regions of the galaxy, the tail's form could shift entirely. Our star is currently traveling through a cloud of interstellar gas known as the local interstellar cloud, but one day, millions of years from now, it will enter another region. When that happens, the glow and tail may change their structure completely, reshaping the bubble of our cosmic home. For humanity, this discovery was profound not because it changed daily life, but because it revealed something intimate about our place in the galaxy. We are not stationary, we are passengers on a moving world, inside a moving bubble, inside a moving galaxy. The green glow around our solar system is the mark of that motion, a sign that we, too, leave a trace as we travel. Voyager's journey showed that even the emptiest parts of space are full of echoes of motion, memory, and energy. As Voyager continued its drift, scientists began using its data to fine-tune these cosmic weather maps. Each subtle change in plasma density hinted at how the solar wind bent and curved around the helioctail. It was as if the spacecraft were tracing invisible lines of pressure with its instruments, sketching the outline of our solar bubble from within. The result was not a perfect shape but a living, breathing boundary, full of folds and tendrils like the edge of a great nebula. The thought that our Sun had a tail sparked imagination across cultures and sciences alike. Some artists painted it as a glowing comet trailing green and gold, while others saw it as a kind of cosmic aura, proof that even stars wear crowns of light. For scientists, it became a new field of study, heliospheric astrophysics. By comparing our Sun's bubble with those of other stars, researchers could begin to understand how cosmic rays shape planetary systems and how interstellar environments affect the habitability of worlds. Over time, the models grew ever more intricate. The helioctail seemed to divide into two main lobes, one dominated by positively charged particles and the other by negative ones, twisted together in vast spirals. The green glow was strongest where these flows met, producing a soft radiance that flickered faintly with every solar cycle. If we could see it with our eyes, the night sky would show not just stars, but a gentle emerald haze stretching away in the direction opposite our Sun's motion. Voyager's silent movement through this environment turned data into poetry. Each pulse of plasma it detected hinted at the unseen beauty around it, the glowing currents, the invisible tides, the tail that marked our passage. The spacecraft was a blind traveler among wonders, feeling rather than seeing, yet revealing truths no human instrument had ever touched before. Its measurements allowed Earth to imagine what it could never behold directly, the shimmering footprint of our solar system moving through eternity. The green glow was not just a discovery, it was a reminder of connection. It showed that even at the scale of galaxies, light still ties things together, that motion, magnetism, and matter are part of one vast, harmonious dance. The tail and the glow are our Sun's way of speaking to the universe, saying, "I am here, and I am moving." Through Voyager's distant whispers, that message returned home, subtle and beautiful, across the silence of light years. Today, scientists continue to refine their understanding of this cosmic structure. Each new mission builds upon Voyager's legacy, mapping the heliosphere with increasing precision. But even as knowledge deepens, the mystery remains enchanting. The green glow and the hidden tail remind us that we are not adrift in emptiness but enveloped in motion, light, and unseen grace. The Sun's passage through space is not silent, it leaves a luminous trail that tells the story of our existence. And somewhere far beyond the planets, Voyager still drifts within that glow, feeling the gentle brush of interstellar wind. Its instruments continue to record the quiet shifts of plasma, the faint tremors that define the outer frontier. It may never see the green light or trace the full length of the tail, but through it, we do. Through its endurance, we glimpse the true shape of our home in the galaxy, a glowing bubble, alive with color and movement, trailing softly behind a wandering star. When astronomers first noticed the object, it looked familiar enough, a bright speck with a long, fading trail moving against the backdrop of stars. Yet even in those early observations, something about its behavior refused to fit neatly into the usual patterns of a comet. Most comets followed predictable curves, their tails responding to sunlight and solar wind in well-understood ways. This one shimmered oddly, its brightness fluctuating as though pulsing with a hidden rhythm. It seemed to move not like a passive wanderer but as if something within it were subtly stirring. Scientists soon began comparing its orbit to those of known comets, but the numbers didn't align. It wasn't bound to the Sun in a closed ellipse, it was flying in on a hyperbolic trajectory, meaning it would visit once and never return. That alone wasn't unheard of, but its speed and angle made it truly remarkable. It wasn't falling in from the distant Oort cloud, like most long-period comets, it was entering from far beyond, from interstellar space. This realization turned what seemed like an ordinary comet sighting into a cosmic event, the first known visitor from another star system. As the weeks passed, telescopes around the world turned toward it, each gathering data that deepened the mystery. Instead of producing a thick, fan-shaped tail, the object emitted faint jets of gas that appeared to shift direction unpredictably. Its surface composition was strange, reflecting light in a way that didn't match typical ice-dust ratios. When sunlight hit it, instead of heating evenly, it released bursts of vapor in pulses, as though vents beneath its crust were opening and closing irregularly. No known comet behaved this erratically. The international astronomy community quickly rallied, sharing data in real time. Observatories from Hawaii to Chile to space-based instruments began tracking every flicker. The more precisely they measured its path, the more confounding it became. Even after accounting for the gravity of the Sun and planets, the object was accelerating slightly, as if something was pushing it outward. That gentle, steady acceleration was too weak for engines or technology, yet too consistent to ignore. It was as though the comet were being nudged by invisible hands. At first, some wondered whether the cause was outgassing, jets of vapor pushing the body forward as sunlight heated it. That would be normal for an icy nucleus, except this object showed none of the visible coma that typically accompanies such activity. It looked almost dry, like rock or metal, but it was still accelerating as if propelled. This contradiction baffled even seasoned comet specialists. If it was shedding material, it was doing so in a hidden, almost stealthy way, quiet puffs of gas or dust invisible to telescopes. Because of its unusual path and motion, people began to imagine possibilities far beyond the usual explanations. Could it be artificial, a fragment of some ancient alien probe or debris drifting between stars? Though scientists urged caution, the mystery invited curiosity. The shape, as best inferred from its light curve, was elongated, perhaps 10 times longer than it was wide, tumbling end over end like a shard of glass. It had no clear symmetry, and its spin seemed oddly irregular, as though it had been tossed rather than borne. The name given to it, Oumuamua, meant a messenger from afar arriving first. It was a poetic acknowledgement of both its origin and its singularity. This wasn't just another comet, it was the first interstellar visitor humanity had ever recorded. It carried with it the chemical fingerprints of another system, perhaps the debris of a shattered planet or the remnant of a distant collision. Whatever its story, it had traveled for millions, maybe billions, of years through the quiet dark before brushing past our Sun. As data poured in, scientists began modeling how such an object could form. Some proposed that it was a fragment of nitrogen ice, chipped off a Pluto-like world long ago. Others suggested a porous carbon-rich structure that could shed gas invisibly when warmed. But each idea came with problems, none fully matched the observed acceleration, reflectivity, and spectral readings. Oumuamua remained a puzzle wrapped in light, refusing to fit neatly into the categories of comet or asteroid. Its tail, or rather, the lack of a traditional one, was one of its strangest features. Instead of a long plume extending directly away from the Sun, it seemed to emit only a faint, asymmetric haze. Some infrared instruments detected almost no dust at all. It was as if the object were exhaling vapor without scattering visible material, a behavior unprecedented in any comet observed before. This meant it was shedding molecules so small or sparse that they escaped detection, yet enough to alter its course. Voyager's distant data added a poetic resonance to this discovery. Both the spacecraft and Oumuamua were wanderers crossing boundaries between stars. One was built by human hands, the other, shaped by cosmic chance. As scientists compared notes, they realized that what Voyager was revealing about the edge of our solar system, its invisible fields and gentle winds, might also explain how such interstellar travelers move. Oumuamua's strange drift could be influenced by the same delicate forces Voyager was now measuring in deep space. In time, researchers noticed something subtle. The object's reflectivity increased as it neared the Sun, suggesting that its surface wasn't solid rock but perhaps a thin layer of volatile material, possibly hydrogen or carbon dioxide frost. When that material sublimated, it could provide gentle thrust without producing visible gas. That idea fit the physics, though it raised another question: how could such fragile material survive the harsh interstellar journey? Its resilience was almost paradoxical. The tumbling motion of Oumuamua was equally perplexing. Instead of spinning smoothly, it wobbled chaotically, suggesting that it had been struck or reshaped by collisions long ago. Some simulations showed that such motion could only persist if the object were extremely rigid or strangely shaped, perhaps like a pancake or a cigar. The changing brightness implied sharp angles and flat facets reflecting sunlight at unpredictable intervals. The more they studied it, the more it resembled something sculpted rather than random. Still, scientists resisted sensational explanations. They worked methodically, comparing Oumuamua's trajectory to hypothetical objects made of ice, dust, metal, or even porous organic foam. None matched perfectly. Each model explained some data and contradicted others. The mystery became a mirror for human imagination, a reminder that even in an age of precision astronomy, nature could still surprise us with forms and behaviors beyond expectation. Months passed, and Oumuamua drifted farther from the Sun, dimming until no telescope could see it. It had left as quietly as it had come, carrying its secrets away into the black. But the questions it raised lingered like an echo. Was it an ordinary object behaving extraordinarily, or something genuinely new, a type of interstellar body never before imagined? In the silence that followed its departure, astronomers debated, speculated, and dreamed. The encounter left a mark on science itself. It pushed astrophysicists to refine their models of interstellar debris, to consider materials and forces that had once seemed too exotic to matter. It sparked new missions designed to catch the next visitor before it sped away. The event taught researchers humility, that even with all our telescopes and theories, the cosmos still held surprises vast and subtle, waiting to rewrite our sense of what was possible. Later studies using powerful instruments like the Hubble Space Telescope confirmed that the object's acceleration could indeed be explained by outgassing if the material escaping were extremely small and invisible, such as molecular hydrogen. That would mean Oumuamua was a piece of frozen hydrogen ice, something never before observed. If true, it would be a fragment of unimaginable delicacy, drifting across light years without melting, a feather on the galactic wind. Others found that idea too fragile. They argued that the object might instead be a thin, natural sheet of material, perhaps a sliver of carbon-rich dust compressed by radiation in another star system. Such a sheet, only millimeters thick but kilometers wide, could behave just as observed, reflective, light, and responsive to sunlight's pressure. This model made Oumuamua the first known example of a light sail formed not by intelligence, but by cosmic chance. Whatever its true nature, the comet that didn't behave like others changed how humanity looked at space. It showed that the distances between stars aren't completely empty, that fragments of alien worlds can wander across the galaxy and briefly pass through our skies. It reminded us that our solar system isn't isolated but part of a larger, restless network of motion and exchange, where even the smallest stones can carry the stories of other suns. As Voyager drifted through the outermost reaches of the heliosphere, scientists often imagined it crossing paths with such visitors, two messengers from opposite directions, passing silently in the cosmic dark. One carrying human fingerprints, the other carrying the memory of another world. Both symbols of motion, curiosity, and the fragile persistence of matter across time. The thought was humbling and strangely comforting. Oumuamua's visit may have lasted only months, but its legacy endures in every new search for interstellar travelers. New instruments, tuned to scan the sky for fast-moving, hyperbolic paths, now watch constantly. When the next object arrives, humanity will be ready to observe earlier, follow longer, and perhaps even send a probe to meet it. The lessons learned from the first messenger paved the way for encounters yet to come. In the quiet of deep space, both Voyager and Oumuamua drift onward, each carried by unseen winds. One is fading into the interstellar medium, transmitting the last faint murmurs of Earth. The other is already far beyond reach, reflecting the light of no star. Yet both share the same truth. They are part of the endless exchange between systems, a dance of dust and metal, of ice and curiosity, that links the galaxy together. In the end, the comet that didn't behave exactly like others became a symbol of cosmic unpredictability. It whispered to humanity that not all visitors announce their nature clearly, that sometimes strangeness is its own kind of message. Its fleeting glow, its mysterious push, and its silent retreat all reminded us that the universe remains vast and unsolved, a place where every answer carries the echo of another question still waiting beyond the stars. When astronomers plotted the trajectory of the strange visitor, they expected its path to follow the clean geometry of gravity, a perfect arc dictated by the sun's pull and the quiet influence of the planets. Yet, as they refined their calculations, something subtle but persistent began to appear. The object wasn't obeying gravity alone. It was being nudged, just slightly, by an invisible force. These deviations were so small that at first they seemed like measurement noise, but the pattern was too consistent to dismiss. The comet, if it could even be called that, was drifting as though under the touch of a faint, continuous breath. Each new observation tightened the mystery. The changes in speed and direction were minuscule, no more than a few millimeters per second, but over millions of kilometers. Even that was enough to shift its trajectory noticeably. Ordinary comets experience similar effects due to outgassing, the release of vapor as sunlight warms their icy surfaces. But this one didn't show the usual visible plumes or tails. The tiny pushes appeared without evidence of jets or dust, as though the force was there but the cause was hidden from view. Scientists began testing every explanation they could imagine. Could sunlight alone be pushing it, radiation pressure acting on an unusually thin body? If the object were flat and lightweight, sunlight could indeed provide a steady acceleration. The math worked surprisingly well. But such a shape would have to be extraordinary, a sheet only a few millimeters thick and tens of meters across. It sounded less like a comet and more like a sail, an image that stirred both awe and disbelief. Others clung to more conventional explanations. Maybe the gas jets were simply too faint to detect, composed of molecular hydrogen that left no visible signature. If so, the object could still be natural, a fragment of frozen hydrogen ice ejected from the surface of some distant, Pluto-like world. When sunlight struck it, even the smallest amount of sublimation could produce thrust. Yet this idea also seemed fragile. Hydrogen ice would evaporate quickly in interstellar space, unable to survive the long journey between stars. As scientists debated, the data remained steady and indifferent. The object was moving exactly as observed, gently, persistently accelerated by something beyond gravity. Its motion became a quiet symbol of cosmic subtlety, a reminder that even the smallest forces, given enough distance and time, could alter a traveler's fate. In the emptiness between stars, a single molecule leaving the surface of a rock could shift its path forever. Nature's hand was patient, precise, and impossibly light. The phenomenon of non-gravitational acceleration was not new, but it had never been seen like this. In typical comets, the effect is accompanied by bright jets and visible fans of material streaming away. Here, nothing. The acceleration was smooth and symmetrical, not jittery or chaotic. That regularity ruled out random venting. It suggested a uniform cause, something acting evenly across the surface. It was as if the entire object was being pushed gently from one side, like a leaf caught in a steady, invisible breeze. The more astronomers looked, the more they realized how delicate the universe could be. Space seemed empty, yet here it was filled with forces so fine that only a visitor from beyond could reveal them. The sun's photons, each a packet of light with the tiniest push, were capable of nudging worlds and wanderers across light years. These tiny pushes, repeated endlessly, could sculpt orbits, twist rotations, and send interstellar debris drifting into new destinies. In that way, the object's motion was less a puzzle and more a story of cumulative grace. Back on Earth, computer models ran day and night. Scientists simulated 1,000 different materials, densities, and shapes. Some modeled it as a flat shard, others as a hollow shell, and still others as a porous clump of organic foam. Each model told a different version of the same tale, that even a faint emission or a whisper of light could guide an object's path across the stars. The smallest difference in composition could mean the difference between a comet and a cosmic sail. Some theorists suggested that perhaps the object was spinning in a way that made it seem to accelerate. If its rotation changed how sunlight reflected off it, the measured trajectory might appear distorted. But this explanation, while clever, didn't fit the data perfectly. The acceleration persisted even after accounting for rotation. It was a real force, not an illusion. Something truly was pushing the object, and though humanity could calculate its strength precisely, the source itself remained invisible. It was this combination of precision and mystery that gave the event its strange beauty. Everything about the object obeyed physics, and yet every detail defied intuition. The forces at work were familiar, but their expression was unique. Each new observation added another layer of understanding and wonder, as if the cosmos were reminding us that truth often hides in gentleness. The object's quiet push was the universe whispering in equations rather than thunder. In time, researchers began to see parallels with Voyager's own experiences. The spacecraft, too, had been subject to tiny, constant forces, solar radiation, thermal emissions from its own body, the drag of charged particles. Over decades, even those subtle influences had shifted its path by measurable amounts. Voyager's engineers had learned to calculate and correct for them. Now, those same principles were being applied on a grander, more mysterious scale to understand a visitor from another world. It became clear that the cosmos itself is a web of invisible nudges. Every particle of light, every puff of plasma, every field line and ripple in the magnetic sea exerts its influence. The path of a comet, a probe, or even a planet is never purely mechanical, it's sculpted by 1,000 whispers. The interstellar visitor's motion was a perfect demonstration of this truth, a delicate dance of forces almost too small to imagine, yet powerful enough to rewrite an orbit. For the scientists studying it, the process was humbling. They were not uncovering grand explosions or massive gravitational waves, but something much more subtle, the art of persistence. The lesson was clear: the universe doesn't only shape itself through violence, it also works through patience. Over eons, gentle forces can move mountains of stone and ice, can change paths across entire systems. The visitor was proof that endurance and smallness could hold cosmic power. As debates continued, new theories arose that blended science and imagination. Some thought it could be a fragment of a shattered interstellar planetesimal, a remnant of a system long gone cold. Others speculated that such objects might be common, thousands of them passing through the galaxy at any given time, each pushed by faint pressures of light. Perhaps the universe was full of these messengers, but only now were our eyes sharp enough to notice. If sunlight was the sculptor, then the object was its canvas. The shape, rotation, and composition all interacted with the steady flow of photons, each impact transferring momentum. Over millions of years, such forces could spin, stretch, and launch it toward distant suns. It was as though light itself had been its ship and current. The thought was almost poetic, that a body born in the dust of one world could sail the light of another across the galaxy. In the months following its discovery, astronomers turned to the future. They began designing new telescopes capable of detecting similar travelers earlier, when they were still far from the sun. The goal was to catch them before they sped away, to study their composition, trajectory, and faint forces in greater detail. Oumuamua had taught them that not all discoveries come with fireworks. Some arrive as whispers, fleeting but transformative, their lessons carried in the smallest changes of motion. The tiny pushes that shifted the object's path also shifted something within science itself. They blurred the line between comet and craft, between natural motion and the subtle artistry of cosmic physics. Even the most skeptical researchers found themselves moved by the beauty of precision, the idea that every movement in the heavens, no matter how slight, is part of a vast and interconnected fabric. The visitor had given them not just data, but perspective. In time, the object faded from view. The telescopes that had tracked it with such care could no longer find its faint light. Yet, its influence lingered. The numbers it left behind, the residuals of its motion, continued to whisper their story. They became a kind of cosmic fingerprint, proof that even in the near-perfect silence of space, motion is never entirely unforced. Every traveler, whether stone or machine, feels the breath of the universe on its back. Voyager's continued journey echoed this truth. Decades after launch, it too was being shaped by forces unseen. The faint heat from its generators, the radiation from the sun now far behind it, the tug of interstellar particles all left measurable marks. Both Voyager and the interstellar visitor shared a kinship in motion, shaped not by destination but by the endless conversation between energy and matter. They were both proof that everything moves not in isolation but in harmony with the whole. Scientists began to realize that this subtle interplay might be universal. Every star, every dust grain, every comet feels it. Over billions of years, such forces sculpt galaxies, bend cosmic filaments, and nudge planets into resonance. The visitor's small accelerations were not exceptions, they were reminders. What we call stillness is only a balance of many pushes too fine to see. The universe is always breathing, always moving, even in its quietest corners. As the years passed, the debates quieted but the fascination endured. Some still favored exotic explanations, others trusted the slow accumulation of evidence pointing to natural origins. In the end, the exact nature of the tiny pushes mattered less than what they revealed about our ability to notice them. Humanity had learned to measure the almost immeasurable, to feel the touch of light across millions of kilometers and understand that it carried meaning. That understanding rippled outward, inspiring a new generation of physicists and astronomers to look for the smallest signatures in vast data sets. Just as Voyager had revealed the faint hum of interstellar plasma, the study of the visitor's motion taught researchers to listen for the quiet movements hidden between the noise. Every shift in trajectory, every deviation from gravity alone, became a clue to the invisible structure of reality. Even now, when scientists simulate the visitor's passage through our solar system, they marvel at the elegance of its path, a perfect story written by imperceptible hands. Each slight deflection, each infinitesimal drift, adds up to a journey across the stars. The object may have left our sky, but the trail of equations it inspired remains, guiding new explorations of light, motion, and interstellar matter. In a way, the tiny pushes that shifted its path also shifted ours. They reminded us that discovery is not only about the loud and the spectacular, but also the delicate and the quiet. The forces that move galaxies are the same ones that nudge dust, probe, and comet alike. Through this understanding, we saw that even the faintest light, traveling through infinite darkness, carries power enough to change the course of a traveler and, perhaps, of thought itself. And so, as Voyager drifts onward and the interstellar visitor fades into distance, both continue to move under the same silent forces, the breath of starlight, the touch of plasma, the gravity of unseen worlds. Their journeys are guided not by will, but by wonder. The universe, vast and patient, teaches through the smallest gestures, and sometimes it takes a visitor like this to remind us that motion, in all its quiet beauty, is the language of the stars. The moment the discovery of the strange interstellar visitor was confirmed, observatories across the world sprang into action. Every major telescope, from the sprawling mirrors in Chile's Atacama Desert to the icy domes of Mauna Kea, pivoted toward the faint, fast-moving point of light. Astronomers knew they had little time. The object was already racing away from the sun, its brightness fading with every passing hour. Each observation mattered, every second counted. The global scientific community felt as if the universe had handed them a once-in-a-lifetime visitor, and all they could do was watch as it hurried past. Teams coordinated through instant networks, sharing coordinates, velocities, and spectra almost in real time. Normally, the process of studying a new object took weeks of scheduling and calibration, but this time the pace was electric. It was rare to see such unity among researchers scattered across continents. People who normally competed for telescope time now worked like a single organism with many eyes. The object's path was calculated again and again, each update refining its orbit and confirming what everyone hoped wasn't just an error, it truly came from beyond our solar system. In Hawaii, the Pan-STARRS telescope had been the first to detect it, but now instruments like the Very Large Telescope in Chile and Hubble in orbit joined the pursuit. They gathered light in all wavelengths, visible, infrared, ultraviolet, trying to extract every possible clue from the faint glow. Even radio telescopes joined, just in case the visitor emitted something unexpected. 4 days, nights blurred together in command rooms lit by monitors showing a single moving speck crossing the starry background. Each telescope added a piece to the puzzle. From one, they learned how its brightness changed as it spun; from another, what colors of light it reflected; from a third, how sunlight seemed to scatter unevenly from its surface. When all the data was compared, a strange picture emerged. The object wasn't spherical or even potato-shaped like most asteroids. It appeared elongated, perhaps 200 meters long and less than 30 wide. Its rotation was uneven, tumbling rather than spinning smoothly, as if it had been tossed through space like a stick caught in invisible waves. Astronomers spoke in hushed awe. They had never seen anything like it. Even with thousands of known comets and asteroids in their catalogues, none had ever displayed this combination of brightness, shape, and motion. Every night brought new measurements and fresh debates. Could it be metallic? Was it covered in organic dust? Did it have a crust of carbon, or maybe frozen nitrogen? Each answer only led to more questions, and the more they looked, the stranger the object became. The data hinted that its surface was unusually reflective, about 10 times brighter than typical cometary material. That reflectivity meant it was bouncing sunlight away efficiently, perhaps explaining its faint acceleration without visible jets. But what kind of surface could survive a billion-year journey between stars without eroding? Some suggested a hardened crust of carbon left behind as volatile materials boiled away. Others thought it might be an interstellar shard polished by endless collisions with dust and plasma. As the story spread, telescopes beyond the professional realm joined the chase. Amateur astronomers with high-powered instruments trained their lenses on the same patch of sky, contributing valuable timing and brightness data. It was one of those rare moments when professionals and enthusiasts collaborated seamlessly. The excitement transcended borders, languages, and backgrounds. Everyone wanted to glimpse the traveler from beyond, to capture one more bit of light before it disappeared forever. Meanwhile, space agencies reoriented their deep space tracking networks. Even the now aging Spitzer Space Telescope was called upon for a final observation. It tried to detect the object in infrared, hoping to measure its heat emission and estimate its size more accurately. But by then, the visitor had already faded too much. Spitzer's detectors found only silence, confirming that it was smaller and colder than many had expected. The cosmic guest had passed through swiftly, leaving behind only a trail of fading numbers. Still, those numbers were enough to transform astronomy. When the combined datasets were analyzed, they revealed details too delicate for a single telescope to notice. The object's tumbling motion wasn't random. It followed a complex rhythm that hinted at an irregular mass distribution, like a piece broken off a larger body. Its spin slowed slightly as it left the sun, suggesting that sunlight, not internal activity, was influencing its rotation. Step by step, the evidence leaned toward radiation pressure as the mysterious force behind its acceleration. But just as quickly as data arrived, the window for observation began to close. Within weeks, the object dimmed beyond the reach of most instruments. Observatories shifted to other tasks, though few astronomers could fully move on. The visitor had left an afterimage in their minds, a lingering curiosity that refused to fade. They had glimpsed something from another star system, something older than any spacecraft or comet known, and it had slipped through their view almost before they understood what it was. Even as the object receded, telescopes continued to search the skies for others like it. The discovery triggered a new wave of automated surveys, using algorithms capable of detecting fast-moving, hyperbolic paths among millions of data points. Telescopes that once scanned for asteroids threatening Earth now doubled as lookouts for interstellar travelers. The universe, it seemed, might be far more dynamic than once imagined, its pathways crisscrossed by fragments of alien worlds quietly drifting between suns. As new images came in from the final days of visibility, astronomers stitched them together into short animations showing the visitor's motion. Against the static field of stars, the object moved like a glowing ember, its light flickering rhythmically as it spun. The animation was mesmerizing in its simplicity. Somewhere, that faint dot carried the chemical memory of another solar system, dust and molecules shaped by a different star, now whispering past ours. It made the cosmos feel both intimate and vast all at once. For weeks, observatories continued comparing notes. Spectrographs revealed no clear sign of water or carbon dioxide, substances common in most comets. Instead, there were hints of complex organics, carbon-rich compounds that absorbed blue light and reflected red, giving the object its warm hue. These same compounds coated asteroids in our system, but never in quite the same concentration. The differences suggested an origin story written under another sun's chemistry, perhaps older, colder, and slower than ours. Even as the scientific results grew more detailed, there was an emotional undercurrent to the work. Many astronomers had spent their entire careers mapping predictable motions, asteroids, moons, stars that followed well-understood rules. But here was something from elsewhere, something that did not belong yet felt entirely natural. It was a humbling experience. For the first time, humanity had evidence that the galaxy's vast distances were not empty divides, but pathways that matter could cross. In the quiet control rooms, the mood often bordered on reverence. Scientists who had spent decades interpreting data found themselves pausing simply to look at the faint streak on their monitors. The realization sank in. This speck of light had come from a place no human instrument had ever reached, carrying no message, no technology, just the silent proof of cosmic continuity. In its passing, it connected two stars separated by millions of years and trillions of kilometers. The collaboration also set new standards for how astronomy operated. The event showed that speed and cooperation were as crucial as technology. Because of the object's fleeting brightness, teams learned to share data instantly, without hesitation. A culture that often prized individual discovery shifted, if only briefly, toward collective effort. That transformation outlasted the event itself. The legacy of those weeks was not just scientific, it was human. With the visitor now gone from view, researchers began reconstructing its story backward, using the collective data to trace its path across the galaxy. By modeling its incoming direction, they found that it likely came from a region near the bright star Vega, though the timescales were too vast to know for sure. Over hundreds of millions of years, gravitational encounters could have nudged it from any number of systems. It might even have passed through interstellar clouds that polished or reshaped it before it reached us. In this sense, every telescope that turned toward it was not just observing an object, but a timeline, a record of cosmic events older than Earth's continents. Each spectral reading was a page from a story that began in another sun's debris field, perhaps after a planetary collision, perhaps after a dying star flung its fragments outward. The light bouncing off it was ancient sunlight reflected by alien matter, arriving here just long enough for us to notice before vanishing again. As more observatories processed their archived data, a deeper picture began to form. The object's spin axis, its brightness variations, and its peculiar acceleration all pointed to one truth: the cosmos was capable of producing things we had never imagined. What had once seemed improbable, a fragment crossing the stars, was now proven fact. The event had broadened astronomy's vision, forcing it to see not just within systems, but between them. And as if in poetic symmetry, Voyager's instruments, far beyond the planets, were quietly recording the same cosmic winds and dust that such travelers would encounter. The spacecraft, still whispering faint data back to Earth, seemed to echo the visitor's experience in reverse, one born in another system heading outward, the other born here and moving away. Together, they formed a bridge between stars, one passing inward, the other outward, both guided by invisible tides. The telescope's last images of the object became symbols of a new era. The world realized that astronomy had crossed a threshold. We were no longer just observers of our solar neighborhood, we were participants in a galactic exchange, however fleeting. What began as a brief flicker in the Hawaiian sky had opened humanity's eyes to the vast migration of matter across space. The realization changed how scientists thought about planetary systems, survival, and cosmic time itself. Some nights, astronomers who had taken part in those frantic days still revisited the archived data, tracing the object's light curves as though retracing a memory. They described it like remembering a passing train scene. Once through fog, bright, fleeting, and gone before you truly grasp its size. The sense of wonder it left behind was deeper than the data itself. It was the awareness that the universe had reached out briefly to be seen, and humanity had, for once, looked up in unison. Even as the visitor disappeared beyond the reach of all instruments, its discovery ensured that telescopes would never stop searching. The same global network now scans the heavens for faint, fast-moving points that might hint at the next interstellar traveler. Scientists know it will happen again, perhaps soon. And next time, they will be ready, telescopes already pointed, instruments calibrated, humanity's collective gaze waiting for another messenger from the stars. The moment telescopes everywhere turned their eyes toward that wandering light, they turned our own eyes as well. For a brief time, the whole world shared a single question: what else drifts between the stars, unseen? And though the answer may still lie out there, the search continues, a promise written in light, in curiosity, and in the quiet unity of every eye that once looked upward together. When the data about the interstellar visitor was released to the public, it ignited a storm of interpretations. Scientists, journalists, and curious minds everywhere leaned into their screens, each searching for meaning within the numbers. The official reports described unusual acceleration, strange reflectivity, and an elongated shape, but the explanations varied wildly. Some saw it as a natural fragment of rock, others as a piece of frozen hydrogen, and a few whispered something more daring, that perhaps it was a relic of intelligence, a drifting artifact from another civilization. For most astronomers, the first instinct was caution. Extraordinary claims required extraordinary evidence, and no one wanted to leap into speculation that might stain the discipline with sensationalism. But at the edges of discussion, the boundaries of reason were gently tested. What if this acceleration wasn't due to natural causes? What if, they wondered quietly, sunlight was pushing against something thin and artificial, like a sail? It was not an assertion, just a curiosity. Yet in the world of headlines, even a whisper could sound like a declaration. Some researchers argued that such speculation was healthy, that science thrived on questioning the edges of the known. Others warned that too much imagination too soon could cloud perception. The debate was as old as science itself: how to stay open-minded without losing rigor, how to dream without drifting into myth. The visitor, silent and featureless, became a mirror for humanity's own scientific temperament. It tested not only our instruments but our discipline, revealing how wonder and skepticism coexist uneasily in the same mind. The wildest idea came from a respected physicist who suggested, half seriously, that the object could be a kind of light sail, a device propelled by starlight. He didn't claim it was built by aliens, only that its motion was consistent with something very thin and broad being pushed gently by radiation pressure. It was a theoretical fit, not a declaration of intent. But once the word artifact entered the conversation, it spread faster than light. Every media outlet wanted to imagine what it might mean if something artificial had truly arrived from another star. Most astronomers reacted with restraint. They combed through the math again, searching for simpler explanations. Perhaps the object's surface was covered with volatile compounds that sublimated invisibly, creating a faint thrust. Or maybe the shape itself caused uneven reflection of sunlight. The mystery wasn't proof of anything extraordinary, just a sign that we didn't yet know enough. Still, the possibility that it could be something beyond our imagination lingered quietly, like a shadow that refused to leave the room. Amid the speculation, the tone of the scientific papers remained measured. Their language was filled with cautious verbs: suggests, indicates, could imply. These words were chosen carefully, each one protecting the fragile line between inquiry and conjecture. The community knew that one reckless statement could set back decades of credibility. Yet in private, some admitted that even the act of considering artificial origin, however remote, gave them goosebumps. After all, wasn't science meant to stretch curiosity until it brushed against the unknown? For the general public, however, caution was far less appealing. People yearned for wonder, for mystery with meaning. News outlets spun phrases like alien probe and interstellar messenger, feeding a hunger for cosmic connection. Social media magnified the excitement, and soon the visitor became a symbol, part mystery, part mirror of human longing. It wasn't enough that it came from another star, it had to come for something. The silence of space was too empty a story for the imagination to accept. In university halls and late-night discussions, Scientists debated not just the object but the nature of evidence itself. Could one ever rule out intelligence, or was it forever an open door? The question blurred the boundary between science and philosophy. A few argued that the only responsible stance was to acknowledge uncertainty, while others warned that even framing the question in those terms risked turning astronomy into theater. The visitor was testing humanity's intellectual humility as much as its instruments. The idea of an alien artifact persisted not because it was proven, but because it was unfalsifiable. There was simply no way to confirm or deny it definitively with the data at hand. The object had already faded beyond detection, leaving behind just enough mystery to fuel endless speculation. Like a riddle whispered by the cosmos, it offered clues but no resolution. Scientists who valued precision found this infuriating, storytellers found it irresistible. Some researchers pointed out that similar mysteries had once been solved through patience and better tools. The strange lights of the 19th century Martian canals had vanished once telescopes improved. The pulsar, initially dubbed LGM-1 for Little Green Men, turned out to be a rotating neutron star. History was full of natural phenomena mistaken for the extraordinary. The pattern was clear: mystery first, understanding later. The universe was strange enough without needing imagination to fill the gaps. And yet, imagination refused to stay silent. A few astrophysicists published careful, hypothesis-driven papers exploring how a light sail could behave under radiation pressure. They treated it as an engineering problem, not a claim of alien intent. What thickness of material would create that much acceleration? How would such an object survive interstellar erosion? By turning speculation into mathematics, they turned fantasy back into science. The conversation shifted from "is it built?" to "could such a thing exist?" Meanwhile, other voices emphasized the natural possibilities. Perhaps the visitor was a fragment of a larger body ejected from a planetary collision in another star system. Perhaps it was made of nitrogen ice, a frozen sliver from a Pluto-like world. This idea fit the data neatly. Nitrogen ice could sublimate invisibly, giving the illusion of a push from sunlight. It was elegant, simple, and most importantly, testable in future discoveries. That was the approach most scientists preferred: no poetry, just physics. Still, the tension between the ordinary and the extraordinary lingered. Every discussion seemed to circle back to what it meant to be open-minded. If we dismiss wild ideas too quickly, do we risk missing something profound? But if we embrace them too easily, do we risk drifting into fantasy? The visitor hovered at that boundary, a silent reminder that progress often comes from balancing skepticism with wonder. Each explanation, mundane or marvelous, revealed something about the people proposing it. The physicist who had first suggested the light sail idea grew weary of the media frenzy but stood by his reasoning. He reminded interviewers that his job wasn't to declare truth but to interpret data. If an unusual acceleration fit one model better than another, it was worth considering. The speculation wasn't about aliens, it was about the limits of our assumptions. And in that way, his argument resonated with a deeper scientific philosophy: never to dismiss a possibility just because it feels uncomfortable. In observatories and classrooms, the visitor became a teaching moment. Professors asked students to model its motion, calculate its density, and propose hypotheses. It became a perfect case study for how science works in real time, how ideas compete, evolve, and are tempered by evidence. Some students preferred the bold explanations, others clung to conservative ones. But all learned that truth in science isn't decided by excitement, it's earned through survival against scrutiny. As time passed and the data cooled, most of the community settled on natural explanations. The simplest models fit the facts well enough. There was no need for alien technology to explain an unfamiliar rock. Yet the story had done something remarkable: it had expanded humanity's imagination without breaking science. Even the most skeptical researchers admitted that, for a brief moment, they had felt the vastness of possibility press close, as if the universe itself had winked. That brief openness left a lasting mark. When, years later, another interstellar object was discovered, this one more clearly a comet, scientists were ready. They had learned from the first encounter how to approach the unknown, with rigor, transparency, and humility. The earlier debates had sharpened their tools and expectations. The memory of the artifact theory served as both warning and inspiration, a reminder that science must dance with mystery, but never let it lead. For the general public, though, the story never truly closed. It remained alive in documentaries, podcasts, and speculative art. People liked the idea that the object might have been a message, or at least a relic from minds older than ours. In a strange way, the universe felt kinder that way, less indifferent, more connected. The truth may have been simpler, but simplicity rarely stirs the soul the way mystery does. And so the visitor became a myth of modern times, wrapped in equations instead of legends. Some scientists quietly appreciated that. Even if the artifact idea was wrong, it had drawn attention to the wonder of space science, inspiring countless young people to look up. The blend of reason and imagination had once built astronomy itself. Perhaps it was only fitting that a passing traveler reignited both. In the end, curiosity, not certainty, was the greatest gift it left behind. In private notes and journals, a few researchers admitted something they never said in papers: that part of them wanted the artifact theory to be true. Not because it was likely, but because it was beautiful. The idea that another civilization's creation had brushed past us, unnoticed for millennia, was both humbling and comforting. It reminded them that exploration was a shared cosmic instinct, that maybe, somewhere, others were watching the stars too. Still, as months turned to years, the scientific tone returned to calm objectivity. Conferences moved on, papers gave way to newer discoveries, and the visitor drifted further into history. Yet the echo of that debate lingered like a faint signal from the edge of hearing. It had revealed how humans react to the unknown, some with restraint, others with wonder, all with an unspoken yearning to understand their place in something vast. In hindsight, historians of science would later call this era a turning point, not for what the object was, but for what it taught about scientific communication. The event had exposed how easily nuance can vanish once wonder touches it, how the quiet language of uncertainty becomes amplified into declarations. It became a lesson in humility not just for scientists, but for all who translate discovery into meaning. In the end, most voices agreed on one truth: the universe had presented us with a riddle we couldn't fully solve, and that was okay. Not every question needs an answer to be valuable. Sometimes, the power of a mystery lies in the space it leaves for imagination. The visitor reminded us that exploration is not only about finding certainty but learning to live gracefully with the unknown. Even now, years later, the debate still drifts through academic corridors and late-night discussions. Some still muse about the light sail hypothesis, others roll their eyes at the thought. But both sides share the same quiet awe when they recall that time when something from another star passed through our solar system, and for a brief moment, every mind on Earth tilted upward together, wondering what it might mean. And somewhere in that shared curiosity, between the wild ideas and the careful caution, science found its balance again. The visitor had not just traveled across the galaxy, it had traveled through human thought, reminding us that every theory, no matter how grounded or bold, is part of a single, ongoing story, the story of how we try to listen when the universe speaks softly. When the interstellar visitor first appeared, it was scientists who led the charge to understand it. But as its story spread and the mystery deepened, the attention of governments and major space agencies soon followed. Officials who normally spent their days dealing with budgets and satellite launches found themselves in briefings about an object from another star. The idea alone carried weight, a material fragment from beyond the solar system, passing within reach of humanity's instruments. It wasn't a threat, but it was an event too significant to ignore. Behind closed doors, meetings began at agencies like NASA, ESA, and JAXA. The questions asked weren't about aliens, as popular rumor liked to imagine, but about science, technology, and opportunity. Could such an object ever be intercepted? Could a mission be designed to chase it down? Could future systems be ready to respond faster the next time? The visitor's fleeting presence made it clear that our current infrastructure wasn't prepared for fast-moving phenomena of cosmic importance. It was a logistical wake-up call. NASA's Planetary Defense Coordination Office, though primarily concerned with hazardous asteroids, also took a quiet interest. Here was something beyond the normal catalogue of space debris, something that didn't follow the gravitational rules of the solar family. While there was no danger, there was immense value in learning from it. Reports circulated about how early detection systems might be improved to spot similar objects sooner, giving scientists and engineers a better chance to react before they faded from view. At the European Space Agency, researchers discussed the implications for future survey telescopes. Projects like the Vera Rubin Observatory and Gaia were already designed to map the heavens with unprecedented precision. Now, there was an added motivation to detect interstellar objects as early as possible. The agencies realized that with just a few more days' notice, the world might have been able to observe the visitor in far greater detail, or even send a small spacecraft to intercept it. Timing had been the greatest enemy. Military and intelligence agencies, too, were quietly briefed, not out of suspicion, but out of protocol. Any unusual object entering the solar system naturally drew their attention. The data, however, was quickly shared with the scientific community. Transparency, in this case, was vital. The object was confirmed to pose no threat and no sign of control or propulsion was detected. Still, the incident reminded governments that cosmic phenomena could attract immense public fascination and even geopolitical speculation. In Washington, small committees convened to discuss what the event meant for future policy. Some saw it as an opportunity to justify further investment in planetary science and space observation. Others wondered whether new protocols were needed for potential unknowns entering the solar neighborhood. Space exploration had always been a blend of science and strategy, and this visitor blurred the lines between the two. It wasn't dangerous, but it made humanity realize how vast and unpredictable the universe truly was. NASA issued several official statements emphasizing the natural explanations first. Their tone was measured and factual, aiming to steady the narrative before imagination took over. The agency's leadership understood that while curiosity was healthy, speculation could spiral quickly. Public trust in space science depended on clarity. Still, between the lines of those statements, one could sense the quiet excitement. They had witnessed something historic, and the agency intended to learn everything it could from it. The idea of a rapid response mission was floated within months. Engineers began sketching theoretical designs for spacecraft that could be launched quickly upon the discovery of future interstellar objects. These missions, they imagined, would use advanced propulsion systems, solar sails, ion drives, or even nuclear thermal engines to catch up to fast-moving visitors. The dream was bold: to intercept the next traveler not just with light, but with instruments. To meet it, rather than simply watch it pass. The concept gained traction as data poured in from international teams. The interstellar object had proven that such visitors were real, not hypothetical. And if one had entered our system, others surely would again. Agencies began considering how to maintain telescopic vigilance, an early warning network of global observatories capable of detecting faint, fast-moving dots on hyperbolic paths. Governments understood that the next one might be larger, brighter, or closer. Preparation was no longer science fiction, it was foresight. Funding proposals soon followed. Research groups submitted requests to study the physics of interstellar travel, how rocks, dust, and icy fragments survive the long drift between stars. Even departments unrelated to astronomy, like materials science and propulsion research, became involved. Could we learn from such an object's structure to design better shields for our own spacecraft? Could its surface chemistry reveal new kinds of matter hardened by cosmic radiation? These were practical questions born from a cosmic event. In the midst of scientific planning, the political dimension began to surface. Lawmakers who had rarely paid attention to astrophysics found themselves being briefed on the possibility of future interstellar monitoring programs. Some were fascinated, others skeptical. But the idea of international cooperation, of telescopes, data systems, and missions that transcended national borders was hard to resist. The visitor had done what decades of diplomacy often struggled to achieve: it united humanity's curiosity under a single cosmic banner. China's National Space Administration took note as well. The country's growing capabilities in space observation and deep space missions positioned it to play a key role in future tracking efforts. Chinese scientists proposed collaborations with Western institutions, suggesting joint missions and data exchanges. The tone was one of shared opportunity, not competition. After all, the cosmos belonged to no nation, and this object's path through our skies had reminded everyone of that profound truth. Roscosmos, Russia's space agency, released its own quiet analysis, confirming the object's trajectory and adding observations from Siberian observatories. Even as political tensions simmered on Earth, the data crossed borders freely. Scientists knew that in space, cooperation was essential. The interstellar visitor became a rare neutral ground, an event where every country's instruments contributed to a global understanding, free from rivalry. It was a moment of rare unity, carried by curiosity rather than politics. Private companies, too, began to see possibilities. Firms like SpaceX and Blue Origin, always dreaming of deep space ventures, took interest in the idea of a fast launch interception system. Engineers imagined reusable rockets capable of carrying small probes on short notice. The notion of catching an interstellar traveler wasn't just poetic, it was technically challenging, commercially intriguing, and a potential milestone for private exploration. The visitor's mystery had seeded innovation in places far beyond academia. Governments soon realized that such events could captivate the public in powerful ways. Agencies started planning outreach programs, documentaries, and educational campaigns centered on interstellar exploration. They wanted to inspire, but also to prepare minds for the reality that our solar system wasn't isolated. The visitor had proven that the universe occasionally sends us guests. Someday, one might arrive close enough for humanity to reach. And that possibility required both vision and readiness. Amid this excitement, security analysts drafted quiet memos about public perception. They knew that talk of objects from another star could easily veer into fear or fantasy. Managing information responsibly was crucial. Governments coordinated with scientific organizations to ensure that updates remained transparent but grounded in evidence. The lesson from early speculation was clear: if communication faltered, conspiracy theories would fill the silence. The balance between openness and stability became part of the new interstellar protocol. At NASA's Jet Propulsion Laboratory, engineers began examining whether existing spacecraft, like the long-lived Voyagers or New Horizons, could be reoriented to study the space beyond the Sun's influence. While none could catch the visitor, they could provide context. Understanding how interstellar dust and radiation behave near the heliopause might help model what such travelers endure. Governments recognized that every mission already drifting into deep space had suddenly become part of a broader, more cosmic project. Over time, the excitement cooled into planning. Meetings turned from speculation to strategy. Agencies drew up blueprints for an early detection network, a global grid of telescopes working together, using AI algorithms to flag unusual trajectories. Governments quietly approved budgets for new sensors, for better sky coverage, for faster data sharing systems. What had begun as a passing visitor was now reshaping how Earth watched the heavens. The ripple effect had become policy. The United Nations Office for Outer Space Affairs, usually focused on treaties and safety, even hosted a special session. Delegates discussed the philosophical and logistical implications of interstellar objects. What if one day a fragment carried biological material? Who would study it? Who would decide its handling? The questions were far from urgent, but they were vital. For the first time, the framework of planetary protection expanded beyond our solar system. The visitor had widened the horizon of responsibility. In parallel, space agencies began sharing their archived data from the event. It became an open resource for universities, research centers, and independent scientists worldwide. Governments recognized that secrecy served no purpose here, collaboration would yield more value. The policy of transparency reinforced trust, both between nations and between science and the public. The visitor had come and gone without warning, but its trace was shaping how humanity prepared for the next whisper from the stars. Years later, when the excitement had faded into history, internal memos revealed how profoundly the event had influenced planning. Budgets for rapid response missions had quietly increased. New telescope arrays were prioritized. The idea of interstellar preparedness became an accepted part of long-term strategy. The visitor had reminded governments that the cosmos doesn't follow our schedules, and readiness requires imagination as much as funding. In think tanks and research institutes, strategists began using the event as a case study. They compared it to historical moments when humanity first glimpsed new worlds, the discovery of exoplanets, the first radio signals from pulsars, the Voyager photographs of distant moons. Each time, the unknown had forced institutions to adapt. The interstellar visitor was no different. It represented not danger, but transformation, the slow realization that humanity was part of a galactic ecosystem, not isolated from it. The event also prompted ethical reflections within space policy circles. Should humanity ever attempt to alter or capture such an object if one passed close again? Would intercepting it be exploration or interference? Legal frameworks had never imagined such scenarios. Treaties written for the Moon and Mars now felt quaintly local. The visitor's brief appearance had stretched the law itself, showing that the frontier of discovery would always outpace regulation. Some governments proposed new initiatives to coordinate interstellar studies under a single umbrella. A few suggested creating an international interstellar observation network, a standing coalition of agencies sharing real-time sky data. Though the name sounded grand, the idea was simple: no more surprises. The next time an object from another star drifted through our system, the world would recognize it instantly, ready to act in unity rather than haste. In budget hearings and parliamentary discussions, skeptics asked whether it was worth the investment. But proponents argued that discovery was the best insurance policy against ignorance. The visitor had proven that the universe interacts with us directly, that the stars occasionally send their fragments across the gulf. To ignore such gifts would be to waste a cosmic opportunity. Slowly, funding followed conviction. Space awareness became not just exploration, but stewardship. Even the more cautious governments admitted the symbolic power of the moment. The idea that humanity had been visited not by life or intelligence, but by matter from another world carried quiet poetry. It reminded leaders, scientists, and citizens alike that the universe does not belong to any one nation. Every telescope that had turned upward that year had looked beyond borders, beyond languages, toward something truly shared. That understanding seeped, subtly, into policy and culture alike. When reports were eventually compiled, they read more like blueprints for a new kind of astronomy than government documents. They spoke of open data, rapid coordination, and ethical responsibility. They framed interstellar encounters not as anomalies, but as invitations. The language was humble but visionary: the next visitor would not catch us by surprise. Humanity would be ready not out of fear, but out of gratitude for the chance to listen again to the universe's quiet knocks. And so, in the years after the interstellar object faded into the dark, the influence of its passing remained. Governments continued to fund deeper sky surveys. Agencies strengthened their networks. The lessons of collaboration endured. For once, a celestial event had united science, politics, and imagination under one shared principle: that to explore responsibly is to be ready, to stay curious, and to keep our eyes open for whatever might drift toward us next from the endless deep between the stars. The news that an interstellar object had passed through the solar system had already captured global attention, but one moment crystallized the public's hunger for connection. A member of parliament, known for her interest in science and technology, formally requested that space agencies release as many images of the visitor as possible. She wasn't asking for spectacle, she wanted the data, the raw visuals, the evidence that humanity had truly glimpsed a fragment from another star. It was a call for transparency and engagement, a recognition that images could carry knowledge beyond words. Her request rippled quickly through NASA, ESA, and other agencies. Internally, scientists debated the merits and risks. Raw images could be misleading if released without context, noise could be mistaken for structure, shadows for features, but they also had an undeniable power. For the public, seeing was believing. Each photo, each sequence, could inspire a new generation of astronomers, engineers, and dreamers. The decision to release them became a balance between education and precision, between awe and accuracy. The first images, released within days, were humble yet captivating. Tiny streaks of light against a backdrop of stars, captured in different wavelengths and from multiple observatories. They revealed subtle variations in brightness as the object tumbled through space, offering glimpses of its irregular shape. Though faint, the images carried immense significance. They were the first visual proof that humanity had encountered a visitor from beyond the Sun's family, a fleeting, ancient traveler recorded in our instruments and immortalized in pixels. The response from the public was immediate and passionate. Social media lit up with amateur analyses, artistic renderings, and discussions about what the images might reveal. Scientists monitored the reactions carefully, noting both the excitement and the misconceptions. Some people imagined spacecraft or alien technology, while others simply marveled at the idea that a piece of another system had drifted past Earth. The images had become a bridge between professional study and personal wonder. Educational institutions seized the opportunity. Teachers incorporated the images into lessons about astronomy, physics, and space exploration. Students were encouraged to calculate the object's speed, estimate its dimensions, and model its tumbling motion. Suddenly, abstract concepts like hyperbolic orbits and non-gravitational acceleration became tangible. A single request from a lawmaker had unleashed a wave of engagement, turning distant science into a shared, interactive experience. Scientists also used the release to highlight the subtle beauty of the cosmos. By combining images from different wavelengths, visible, infrared, and ultraviolet, they could show more than just a dot of light. Variations in color suggested differences in surface composition, helping to differentiate between icy patches, rocky surfaces, and organic-rich areas. While the details were faint and imprecise, they hinted at complexity. The visitor was not merely a rock, it was a fragment of history, a tiny storyteller of another star system. The lawmakers' initiative inspired international cooperation as well. Space agencies around the world coordinated to release synchronized images, ensuring that observers everywhere could see the same frames. This required meticulous planning, matching timestamps, calibrating sensors, and annotating backgrounds to avoid misinterpretation. The effort demonstrated how public interest could catalyze scientific transparency and collaboration, turning an isolated discovery into a collective experience. Some of the most striking visuals came from the Hubble Space Telescope, which managed to capture the object in ultraviolet and visible light during its final pass. The images revealed the subtle flickering of sunlight across its elongated surface, highlighting its irregular shape and the tumbling rotation. Though the images could not resolve fine detail, they were sufficient to fuel both scientific modeling and imagination, offering clues about how radiation pressure might be subtly influencing its trajectory. Ground-based telescopes contributed as well, capturing long exposures that traced the visitor's path across thousands of stars. When stacked and aligned, the images formed a kind of cosmic animation, showing a point of light slowly tracing a hyperbolic arc. Each frame was a testament to patience, calculation, and coordination. Scientists marveled not just at the object itself, but at humanity's ability to track such a faint, fleeting visitor across vast distances. Media outlets seized upon the images, often accompanied by detailed explanations of the physics behind them. Reports highlighted how the object's brightness changed with rotation, how its reflectivity suggested unusual surface properties, and how the tiny non-gravitational accelerations could be modeled with sunlight alone. While some outlets sensationalized the possibility of alien technology, careful reporting often reminded viewers that the simplest explanation was still a natural fragment from another star. The release also prompted new scientific analyses. Independent researchers, using publicly available data, attempted their own calculations of size, shape, and composition. Crowdsourced efforts led to papers exploring plausible density, surface roughness, and the potential for volatile materials. Some amateur astronomers even tried to model the subtle accelerations, providing valuable validation of professional findings. The lawmakers' request had effectively expanded the global research team beyond the walls of formal institutions. A few images revealed something unexpected: tiny streaks near the main body, initially thought to be artifacts or cosmic rays. Some researchers speculated these could be minuscule dust fragments, perhaps shed from the surface due to thermal stress or micrometeorite impacts. While nothing conclusive emerged, the observation sparked lively debate and demonstrated how even faint visual data could provoke deep inquiry into physics, materials, and interstellar processes. The lawmaker's influence extended beyond the release itself. She advocated for establishing an archival system for all future interstellar observations, emphasizing that raw images, not just processed data, could provide long-term value. The proposal gained traction among agencies, suggesting that every future visitor would be documented as thoroughly as possible, ensuring that no subtle clue would be lost to time. Images were not just pictures, they were historical records. Public engagement led to creative interpretations as well. Artists and illustrators used the released images to imagine what the visitor might look like up close, blending imagination with data. While purely speculative, these renderings helped translate abstract scientific phenomena into forms accessible to all ages. Libraries, museums, and online exhibitions displayed these works, showing the visitor as a point of light, a streak across the sky, and even a sculpted elongated body in imagined detail. The boundary between science and art blurred beautifully. The lawmaker pressed agencies to include not only visible light images but also infrared and ultraviolet captures. This approach allowed scientists to estimate thermal properties and infer composition without needing close physical contact. The images suggested a cold, elongated object, tumbling slowly, reflecting sunlight efficiently. While these properties were consistent with some natural explanations, they were also unusual enough to intrigue researchers and the public alike. Every new wavelength added depth, offering a multidimensional view of a cosmic traveler. Data analysis teams worked tirelessly to annotate the images. Each frame was marked with coordinates, exposure details, and context about surrounding stars. This made it easier for scientists to compare observations from different instruments and track the object's trajectory accurately. The process was painstaking, but the result was a cohesive, globally accessible visual record. Future generations of researchers would be able to study the visitor as thoroughly as possible, thanks to this meticulous work prompted by the lawmaker's request. Astronomers also used the release to teach about observational limitations. Even the most advanced telescopes could not resolve surface detail, and faint accelerations required long-term tracking. By explaining these limitations, agencies helped the public understand the challenge of studying distant, fast-moving objects. The images became a tool not just for curiosity, but for education, illustrating the interplay between technology, physics, and the vast scales of space. The response to the images highlighted a new era in science communication. People didn't just want summaries or press releases, they wanted raw data they could interpret themselves. Citizen scientists analyzed light curves, brightness fluctuations, and orbital paths. The lawmakers' insistence on access had transformed passive observers into active participants, creating a global dialogue about the universe and humanity's place within it. Some images showed variations in brightness as the object rotated, producing subtle peaks and valleys in reflected light. These fluctuations hinted at the tumbling nature of the body and allowed scientists to estimate rotation periods. They also offered clues to its internal structure. A consistent reflectivity suggested uniform surface properties, while irregular spikes indicated bumps or elongated features. Each image became a small window into the physics of an object from another star. Astronomers created composite animations from sequential frames, showing the object tracing a hyperbolic arc across the sky. Watching these animations, even briefly, was a visceral reminder of the vast scales involved, the millions of kilometers it traveled while slowly rotating, influenced by sunlight and tiny forces. For the public, these visualizations transformed abstract measurements into something almost cinematic, giving a sense of motion and journey through an otherwise invisible void. The initiative also sparked debates about archival access. Should all interstellar observations be made public immediately, or only after peer review? The lawmaker argued for transparency, suggesting that early access could accelerate discovery, education, and engagement. Agencies agreed, establishing protocols that balanced accuracy with openness. The release of images became a model for future encounters, ensuring that curiosity and rigor coexisted in public science. In classrooms around the world, teachers used the images to inspire problem-solving exercises. Students calculated the object's speed, plotted its hyperbolic orbit, and simulated light scattering across its surface. Some even attempted to model the faint acceleration using simplified assumptions about radiation pressure. The images had become more than photographs, they were instruments for teaching the next generation of scientists to think critically about the universe. Art and science intersected once more as digital artists created interpretations of what the visitor's surface might look like up close, based on light curves and reflectivity data. These renderings, though speculative, grounded in science, gave humanity a chance to imagine the tactile texture of something from another star system. It was a reminder that images were not just data, they were windows for the imagination. The lawmakers' push also prompted agencies to consider future missions. Could an early warning system be paired with rapid response probes? Could images serve as navigational cues for spacecraft? The idea of chasing interstellar visitors, once science fiction, was now a technical challenge framed in realistic terms. Each image collected during the fleeting pass became a piece of knowledge that might someday guide humanity closer to such travelers. Public interest, fueled by images, encouraged new funding streams. Foundations, universities, and private donors supported research into interstellar objects, observational technology, and rapid response strategies. The visitor had created not only scientific curiosity but also financial momentum for space research, proving that public engagement and institutional planning could reinforce each other when visual evidence was made accessible. As the visitor faded from telescope's view, the images remained. They were stored in global archives, meticulously catalogued, and annotated for future researchers. Long after the object had passed, humanity could return to its trail, analyze the data, and learn more about interstellar materials. The lawmakers' insistence had ensured that no observation, no pixel of light, would be lost to obscurity. The moment of engagement became a lasting legacy. And so, the act of requesting images had done more than satisfy curiosity. It had changed how space agencies communicate, how public science operates, and how future discoveries might be handled. Each frame of the interstellar visitor preserved not just light, but a record of humanity's awe, preparation, and desire to understand. In that sense, the lawmakers' question, simple, direct, and insistent, created a bridge between fleeting cosmic phenomena and enduring human knowledge, a bridge that would last long after the visitor vanished. After weeks of intense observation, a curious pause settled over the global scientific community. The interstellar visitor had dimmed, receding ever faster into the distance, leaving telescopes and instruments unable to capture it as effectively. Scientists found themselves staring at empty patches of sky, waiting for data that would no longer arrive. The frenetic energy that had marked the first weeks of discovery gave way to quiet reflection. The pause was not emptiness, it was a chance to step back, review the collected information, and consider what the fleeting encounter had truly revealed about the cosmos. During this pause, attention turned to photographs from less conventional sources. Amateur astronomers, remote observatories, and even archived data from past missions were revisited, revealing traces of the visitor that had been overlooked. Some images had captured its faint glow before it was formally identified, while others recorded subtle streaks in wide-field surveys intended for completely different purposes. By piecing these together, scientists extended the timeline of observations, filling in gaps and refining the object's trajectory with unprecedented precision. These photos from elsewhere were remarkable not only for what they revealed, but also for how they highlighted the decentralized nature of modern astronomy. Data came from dozens of countries, from mountaintop observatories and backyard telescopes alike. Each image, however grainy or incomplete, contributed to a larger mosaic, allowing researchers to model the visitor's rotation, shape, and acceleration with greater accuracy. It was a testament to how collaboration and accessibility could transform disparate observations into a cohesive scientific understanding. The pause itself offered a rare moment for contemplation. Scientists, journalists, and the public alike reflected on the implications of what they had witnessed. A small, icy fragment from another star system had traversed the solar system, And yet, for all its speed and mystery, it left no trace but light. The object had not crashed, collided, or lingered, it had passed like a whisper. That fleeting presence emphasized the scale of the universe, the brevity of our observational window, and the importance of vigilance and preparation for the next encounter. Meanwhile, comparative analysis of the images provided unexpected insights. Subtle differences in brightness suggested that the object's surface was heterogeneous, with patches reflecting light differently as it tumbled through space. Shadows cast by small ridges hinted at an elongated, irregular shape, confirming prior suspicions that it was far from spherical. The images, though indirect, were transforming a point of light into a three-dimensional understanding of a fragment that had journeyed for millions of years between stars. In the midst of reflection, researchers began to re-examine older datasets for potential interstellar visitors that had gone unnoticed. If this object had passed undetected for so long, there could be others hiding in archival data. The pause allowed time for this meticulous, slow work, careful analysis of countless images captured for other purposes, now repurposed to reveal the subtle fingerprints of objects from beyond the solar system. In doing so, scientists realized that discovery was as much about hindsight as it was about immediate observation. The pause also inspired renewed focus on multi-wavelength imagery. Instruments sensitive to infrared, ultraviolet, and radio frequencies were scrutinized for faint traces of the visitor. Each band revealed different aspects of the object: heat distribution, subtle emissions, or light scattering, allowing researchers to reconstruct its physical properties with greater nuance. Though the object could no longer be observed directly, its passage had left a signature across the electromagnetic spectrum, a record that could be interpreted with patience and careful analysis. Public fascination persisted during this quiet period. Educational outreach programs showcased the images from various observatories, illustrating not only the object's path but also the methods scientists used to study it. People marveled at how a tiny, distant fragment could reveal so much about physics, interstellar travel, and solar system dynamics. The pause became an opportunity for reflection, education, and contemplation, a rare moment when the cosmos had given humanity a story that was both scientific and poetic. Even in silence, the universe spoke through these images. Subtle variations in brightness over time suggested tumbling motion, while comparisons of images taken from different locations confirmed the hyperbolic trajectory. By triangulating observations from multiple sources, scientists refined the estimates of the object's velocity, spin rate, and shape. Every photograph, even those initially dismissed as insignificant, became a critical piece of evidence, highlighting how patience and thoroughness could yield insights even after the main event had passed. Some of the most valuable images came from unexpected corners. Surveys meant to monitor variable stars, track satellites, or map distant galaxies had captured faint traces of the visitor. Once re-examined, these frames extended the known path and offered additional data points. It was a reminder that in astronomy, serendipity often intersects with intention. A random exposure taken for an entirely different purpose could suddenly become crucial, revealing information about an object that had eluded direct observation for weeks. The pause also allowed for introspection within the scientific community. Researchers debated interpretations, compared models, and reconciled observations from a variety of instruments. Conferences and online forums buzzed not with immediate observation, but with careful reflection. Hypotheses about the visitor's surface composition, structure, and origin were re-examined in light of the full suite of images. The quiet gave room for rigor, a pause that underscored the importance of methodical thinking in the face of wonder. Images captured from other parts of the world revealed tiny but consistent patterns. Subtle fluctuations in reflected light suggested that the object's surface was covered in irregular patches, possibly remnants of organic material or hardened icy crust. Differences in color and intensity, when analyzed collectively, provided constraints on its composition. The ability to combine data from multiple sources, despite variations in instrumentation, underscored the power of collaboration and careful calibration in modern astronomy. During the pause, computational models were refined using these diverse datasets. Scientists fed images into simulations to estimate rotation rates, density, and surface reflectivity. By doing so, they could test hypotheses about why the object exhibited a slight acceleration not attributable to gravity alone. Images, even those long after the object had faded from view, provided the empirical foundation for models that could explain the subtle non-gravitational forces acting on it. Photographs from elsewhere also provided perspective on scale. Observatories at higher latitudes or in the southern hemisphere had captured complementary angles, revealing how different observing positions affected apparent motion and brightness. This multi-angle approach allowed triangulation, offering a sense of three-dimensionality and improving estimates of size and shape. Even in its absence, the object continued to teach lessons about perspective, coordination, and observational strategy. Amateur astronomers contributed to the archive as well, submitting their own observations. Despite limitations in equipment, some had captured long-exposure images showing faint trails consistent with the object's trajectory. Professional astronomers incorporated these observations into the dataset, validating the approach of open collaboration. The pause became a time when the distinction between professional and amateur blurred, emphasizing that knowledge of the cosmos could emerge from multiple sources simultaneously. The collection of images allowed for retrospective studies of light curves. Brightness variations revealed periodicities in rotation, hinting at a tumbling motion rather than uniform spin. By analyzing these curves, researchers could infer internal structure and mass distribution. Even in the absence of new data, images from past weeks continued to yield new insights, demonstrating that patient examination could uncover layers of understanding hidden within simple frames of light. Beyond scientific utility, the pause and image compilation allowed for cultural reflection. Artists, writers, and educators drew inspiration from the visuals, imagining the visitor's journey across interstellar space. The photographs became symbolic, a way to visualize something entirely alien yet connected to humanity through observation. The quiet period thus reinforced the notion that science and culture are intertwined, each informing the other in profound ways. Government agencies monitored the analysis closely. Reports derived from the combined images informed policy discussions, planning for future interstellar encounters. The data was used to test rapid response strategies and to evaluate observational coverage, ensuring that the next visitor could be studied more effectively. The pause was not merely a lull, it was a strategic moment to integrate knowledge and refine preparation protocols. Some images revealed unexpected features, like faint flares or streaks that were initially considered artifacts. Careful cross-comparison confirmed that these were not instrumental noise but minor dust ejections, perhaps caused by thermal stress. Such observations highlighted the subtle interplay of forces acting on interstellar objects and underscored the importance of meticulous image analysis, even when the object itself was no longer visible. During this period, discussions also turned to archival preservation. Ensuring that images from various observatories, amateur and professional, were stored in accessible, standardized formats became a priority. This would allow future scientists to revisit the data decades later, applying new techniques or theories to extract additional insights. The pause emphasized that the scientific process extends far beyond immediate observation, relying on the careful preservation and interpretation of data. Outreach efforts capitalized on the pause, using the images to engage students and the public in understanding orbital mechanics, light reflection, and observational challenges. Simulated visualizations based on the data allowed learners to see the visitor's path in 3 dimensions, fostering both comprehension and wonder. The images became educational tools as much as scientific records, bridging the gap between abstract physics and tangible visualization. Finally, as the visitor disappeared from all telescopic views, the images served as the enduring trace of its passage. They allowed scientists to continue analyzing, modeling, and theorizing long after direct observation ended. Each frame, taken from multiple angles, wavelengths, and locations, was a testament to human ingenuity, collaboration, and patience. The pause, initially a moment of absence, became an opportunity, a chance to transform fleeting light into lasting knowledge, and to honor the subtle footprints left by a visitor from the stars. The pause and the photos from elsewhere underscored a profound truth. Even when the universe seems silent, it leaves traces that reward careful attention. Humanity's eyes had turned collectively toward the skies, capturing evidence that would inspire discovery, imagination, and reflection for generations to come. The visitor had passed, but the images ensured that its story endured, a quiet lesson in patience, observation, and the enduring power of light. After the initial excitement and the flurry of observations, scientists began to step back and ask deeper, more specific questions. What exactly about this interstellar visitor made it so compelling? The initial fascination with its speed and trajectory gave way to a careful analysis of its physical properties: shape, composition, rotation, and the subtle forces influencing its motion. Each parameter was scrutinized with the precision that only decades of astronomical experience could provide. These details were not just curiosities, they held the key to understanding processes occurring in other star systems. The visitor's unusual shape was a primary focus. Unlike the roughly spherical or irregularly lumpy comets observed within our solar system, this object was highly elongated, suggesting a history of intense formation or erosion processes. Scientists debated whether its shape was a natural consequence of collisions in interstellar space, or the result of rotational stress over millions of years. Understanding its form could illuminate the physics of small body evolution beyond the Sun's gravitational influence, revealing patterns that no local comet or asteroid could. Surface composition was another area of intense study. The object reflected light in a way that suggested it was covered with a combination of rock, ice, and potentially organic-rich compounds. By analyzing light curves across different wavelengths, researchers hoped to infer whether it contained familiar ices, such as water or carbon dioxide, or more exotic materials common in other star systems. Even subtle spectral differences could indicate processes occurring around other stars, providing a window into chemistry outside the solar system. Rotation patterns intrigued scientists as well. Observations showed a tumbling motion rather than uniform rotation, hinting at a chaotic history, possibly involving collisions or tidal forces before it entered our solar system. Modeling the rotation provided insights into its internal structure and density. If its spin was stable, it might indicate a coherent, solid body. If chaotic, perhaps it was loosely bound or fragmented, hinting at extreme events in its interstellar journey. These details mattered, as they could reveal not only its origin but also the general dynamics of small bodies between stars. Acceleration anomalies captured attention almost immediately. Unlike most natural objects, this visitor exhibited a slight non-gravitational acceleration as it passed through the solar system. Scientists speculated that sublimation of volatile compounds, reflecting sunlight, or even subtle interactions with interstellar dust could account for the movement. Determining the cause of this acceleration became a central question. Was it purely natural, or did it hint at something more complex? Understanding this behavior could refine models of interstellar object dynamics. Size estimates, though uncertain, were critical for interpretation. The visitor appeared to be hundreds of meters long, elongated enough to defy conventional cometary norms. Its slender form suggested that collisions or erosive processes had sculpted it in ways not typically observed within the solar system. By comparing these measurements with brightness and reflectivity, scientists could infer density and mass, providing constraints for any theoretical models about its origin and structure. Another focus was its albedo, or reflectivity. The visitor's surface reflected sunlight efficiently, but not uniformly. Subtle changes in brightness as it rotated suggested a heterogeneous surface, perhaps with patches of ice or rock, indicating a complex history. Scientists compared these findings with local comets and asteroids to identify whether its properties were typical of interstellar bodies or entirely unique, offering potential clues about conditions in other star systems. The visitor's trajectory was a fascinating topic as well. Its hyperbolic path clearly indicated it originated outside the solar system, entering on a course that would carry it forever away from the Sun. Scientists studied the incoming angle, speed, and orientation to deduce its probable origin, considering nearby stars and stellar motions. Such analysis could eventually allow them to trace the object back to a parent system, or at least constrain the likelihood of different interstellar regions as its birthplace. Thermal properties became another point of scrutiny. Infrared measurements suggested that the object absorbed sunlight differently across its surface, with slight temperature variations. These data allowed scientists to estimate its thermal inertia and the potential presence of volatile compounds. Understanding how heat affected its surface helped explain its acceleration and also provided insight into its composition, which could indicate whether it formed in a warm or cold environment around its home star. Spectroscopy provided a wealth of information. By dispersing the light reflected from the object into its constituent colors, scientists could detect the presence of minerals, ices, and potential organics. Even though the data were faint and difficult to interpret, small spectral features offered tantalizing hints about its chemical makeup. Researchers compared these spectra to solar system comets and meteorites, searching for familiar patterns or entirely new signatures, which could indicate the diversity of materials in other planetary systems. Scientists were also interested in the visitor's history of collisions. Its elongated shape and tumbling motion suggested it might be a fragment of a larger body, shattered millions of years ago. If true, it could provide information about collisional dynamics in other systems, how small bodies form, break apart, and survive long journeys across interstellar space. This perspective could inform not only astronomy but also models of planet formation and debris evolution around distant stars. Dust ejection and the potential presence of microparticles were scrutinized closely. Images suggested faint emissions, possibly from sublimating material, although these were far less pronounced than in typical solar system comets. Understanding the mechanisms behind these emissions could reveal how the object's surface interacted with sunlight and the interstellar medium, adding layers of knowledge about the physics of such travelers during their journeys. Interstellar radiation effects were another point of interest. Unlike objects within the solar system, this visitor had endured eons of cosmic rays and interstellar particles. Scientists wanted to understand how such exposure affected its surface and internal structure. Could radiation have hardened it, stripped volatiles, or altered chemical compositions? Studying these effects offered a glimpse into processes that occur over timescales far beyond human experience, revealing the longevity and durability of matter traveling between stars. Spin axis orientation was also analyzed carefully. By measuring subtle variations in brightness, researchers inferred how the visitor rotated in space. The orientation, combined with its trajectory, allowed scientists to model forces acting on the object, such as radiation pressure and potential outgassing. Understanding these dynamics was crucial for predicting motion accurately and for comparing the behavior of interstellar fragments with native solar system bodies. The visitor's interaction with solar wind intrigued researchers. Although distant, the charged particle environment of the Sun could subtly influence small, low-mass objects. Scientists modeled how solar wind pressure might affect trajectory and rotation, providing data to improve simulations of other interstellar objects. This also helped quantify the resilience of small bodies against the combined influence of radiation and charged particles over long distances. Internal structure remained largely a mystery, but scientists attempted to infer it through observations. Its tumbling and light variations suggested a solid, coherent body rather than a loosely bound aggregate. Density estimates, derived from mass and volume approximations, helped constrain models of composition and mechanical strength. These properties, combined with shape and rotation, painted a picture of an object remarkably adapted to survive long journeys through harsh interstellar space. The potential for organics was particularly compelling. Even minute amounts of carbon-based molecules could indicate chemical pathways in other planetary systems. Spectroscopic hints, combined with albedo patterns, suggested the possibility of complex compounds on the surface. While nothing conclusive was observed, scientists were excited by the prospect that a fragment of another star system might contain chemical traces hinting at prebiotic processes, deepening the connection between distant space and the study of life's origins. Trajectory simulations were continually refined. By incorporating images from multiple observatories and analyzing non-gravitational accelerations, researchers could model the object's past and predict its future path with high precision. These simulations were not only academically satisfying, they also provided a template for how humanity might respond to similar visitors in the future, ensuring rapid, accurate analysis and potential mission planning. Observations of light scattering were also informative. Scientists studied how sunlight bounced off the surface, revealing roughness, angles, and texture variations. By comparing scattered light patterns to laboratory models, they inferred surface features at scales smaller than telescopes could resolve. These subtle analyses offered a surprisingly detailed glimpse into a body that remained just a point of light in the sky, demonstrating the power of careful measurement. Scientists were interested in its long-term survival as well. How had the object traveled for millions of years without disintegrating? Its cohesion suggested a robust composition, possibly with low porosity or high structural integrity. Modeling such durability informed theories of interstellar debris and offered insight into how other objects might survive in harsh environments, providing a foundation for understanding small-body physics on cosmic scales. Finally, there was the broader implication. The visitor was a messenger, carrying information about the conditions, chemistry, and physics of another star system. Every observation, every analysis of images and spectra, contributed to a larger understanding of the galaxy. Scientists recognized that studying such an object was not just about one fragment, it was about piecing together the story of interstellar material, and by extension, the diversity of planetary systems and processes beyond the Sun. Even as direct observation ended, scientists remained intensely focused on data analysis. Images, light curves, spectral information, and trajectory models continued to yield insights months and years after the event. The visitor's fleeting journey had left behind a lasting legacy, a complex, multidimensional puzzle that demanded the full attention, creativity, and rigor of the astronomical community, connecting humanity to a fragment of another world in ways that would resonate for generations. In summary, scientists were captivated not by spectacle, but by substance. They were interested in composition, shape, rotation, trajectory, internal structure, and the subtle forces acting on the object. Each detail offered insight into physics, chemistry, and the nature of interstellar space. The visitor represented an extraordinary opportunity to study material from another star system up close, even if close meant across vast cosmic distances. Its passage had provided a rare, precious glimpse into the workings of the galaxy beyond our solar system. Despite the excitement and speculation surrounding the interstellar visitor, one thing became immediately clear to the scientific community: there was no evidence of danger. It was not on a collision course with Earth, nor did it exhibit any signs of artificial propulsion or control. Its path was governed purely by gravitational forces, subtly modified by the pressure of sunlight and minor outgassing. Yet even without peril, the object captivated minds across the globe, reminding humanity that the cosmos can inspire or without posing a threat. Scientists emphasized that the visitor's hyperbolic trajectory meant it had come from another star system and would continue onward, never to return. Its fleeting presence was a one-time event, a brush with a traveler that had crossed light-years of empty space to enter our solar neighborhood. The object carried no warning, no hostility, only the story of its formation and journey encoded in its shape, rotation, and subtle reflective properties. Humanity had been lucky to witness it at all. The lack of danger allowed observers to focus entirely on study and reflection. Media coverage, while sensational in some corners, generally relayed that the visitor posed no risk to Earth. Agencies and researchers worked to reassure the public while also feeding curiosity. The narrative shifted from fear to fascination. This rare alignment of events, an extraordinary discovery that was also safe, encouraged open inquiry and collaborative investigation across continents. Public fascination was fueled by images and observations. Even though the object appeared only as a faint streak against the stars, telescopes revealed tumbling motion, slight variations in brightness, and hints of an irregular shape. Each frame was a window into interstellar space, revealing a fragment shaped by unknown processes in a distant system. People marveled at the realization that a piece of another world had drifted past, reminding humanity of the immense scale and diversity of the galaxy. Scientists highlighted the subtle accelerations that puzzled many observers. The small, non-gravitational forces affecting the visitor were entirely natural, likely caused by outgassing or radiation pressure. Even these minor deviations were fascinating, demonstrating how seemingly inert fragments could experience measurable forces across vast distances. Researchers explained that these effects had no danger associated with them but offered an unparalleled opportunity to test physics in real-world, interstellar conditions. The visitors' elongated shape remained a source of wonder. It challenged prior assumptions about small body formation and survival in interstellar space. How had it remained intact for millions of years, traveling between stars, without breaking apart? Its slender form and tumbling rotation suggested a story of resilience, hinting at the forces it endured during its long journey. Scientists studied this shape not for fear, but to uncover the secrets of cosmic endurance. Observers were equally intrigued by the object's surface composition. Light reflected in subtle, uneven ways, suggesting patches of ice, rock, or potentially organic material. Spectroscopy hinted at complex chemistry, offering clues about processes occurring in other planetary systems. While there was no sign of life or technology, the visitor served as a natural messenger, a fragment containing traces of environments far beyond Earth's solar system. The pause after the initial flurry of observations gave scientists time to compare images from multiple observatories. Even as it faded from view, the data continued to provide insight into rotation, trajectory, and reflectivity. Researchers could trace its path precisely, modeling its interaction with solar radiation and interstellar dust. In this sense, the absence of immediate danger allowed a thorough and methodical examination that would not have been possible under urgent conditions. Media outlets highlighted the contrast between risk and wonder. Headlines emphasized that the visitor posed no threat, shifting public attention from fear-driven speculation to curiosity and learning. Articles explained the physics of hyperbolic trajectories, the significance of interstellar origins, and the methods astronomers use to measure faint objects across vast distances. The story became a case study in how science communicates both excitement and reassurance simultaneously. Children and students were captivated as well. Schools and educational programs featured images and simulations of the object's path, rotation, and brightness variations. Teachers explained how a tiny fragment from another star system could carry information about the chemistry and dynamics of distant worlds. The visitor became a tool for inspiring curiosity, emphasizing that exploration and discovery often exist independent of danger, driven instead by the pursuit of understanding. Astronomers reflected on the visitor as a natural laboratory. Unlike hazardous asteroids, it posed no risk but offered lessons about the materials, forces, and processes shaping interstellar space. Its motion provided empirical data for models of small body physics under unique conditions. The lack of threat allowed researchers to focus on hypotheses about formation, longevity, and composition without distraction or urgency, making the encounter both rare and intellectually rewarding. Even amateur astronomers contributed, observing and tracking the object as best they could. While their instruments were limited compared to professional observatories, their participation added to the richness of global observations. These contributions reinforced the notion that exploration does not require danger to be meaningful. Careful observation, collaboration, and curiosity were sufficient to transform a brief encounter into a lasting scientific achievement. The visitor's slow rotation revealed subtle variations in brightness that hinted at its irregular surface. These patterns provided opportunities for modeling internal density and structure. Observers were fascinated by how a simple point of light could encode such complexity. The lack of danger allowed for patient analysis, with each image scrutinized to extract every possible clue about its physical and chemical properties. Scientists emphasized the natural explanations for its behavior repeatedly, both to counter misinformation and to highlight the beauty of physics at work. The object's motion, shape, and light interactions could be explained entirely by known processes: gravity, radiation pressure, and minimal outgassing. Yet these explanations did not diminish the sense of wonder. On the contrary, understanding that a fragment of another star system followed predictable physics made the universe feel both immense and intimately comprehensible. Space agencies used the opportunity to engage the public in citizen science projects. People worldwide could analyze images, track brightness variations, and compare trajectories. The absence of danger meant there was no rush, allowing methodical participation. This collaboration transformed the object into a shared experience, a cosmic event accessible to anyone with curiosity and dedication, highlighting that wonder often thrives in calm, patient observation. The visitor's interstellar origin was the source of continued fascination. Scientists could infer that it had drifted between stars for millions of years, surviving collisions, radiation, and extreme temperatures. The fact that it arrived at the solar system intact inspired discussions about the resilience of matter in space. Its journey reminded humanity that the cosmos was filled with travelers, each with its own history, and that some of them might one day pass close enough for direct study. Even as the visitor faded, the images captured by telescopes worldwide became lasting symbols. They represented a glimpse of something fundamentally alien yet connected to our solar system by space and time. The absence of danger allowed these visuals to be appreciated not with fear, but with reflection and awe. Each streak, each faint glow, reminded observers that the universe could surprise without threatening, inspire without endangering. Research continued on the small, faint accelerations observed in its trajectory. These were attributed to the pressure of sunlight on the irregular surface, subtle outgassing, and minimal interaction with interstellar dust. Understanding these effects was not urgent, as they posed no hazard, but it offered insights into the physical forces shaping objects in deep space. The phenomenon was a gentle reminder of physics at work on cosmic scales. Astronomers also studied the object as part of a growing class of interstellar visitors. It provided a benchmark for future encounters, allowing comparisons between its properties and those of subsequent objects detected entering the solar system. The lack of danger allowed the visitor to serve purely as a reference and inspiration, teaching scientists about detection strategies, observational techniques, and the behavior of objects that traverse interstellar space. Outreach programs emphasized wonder over risk. Public lectures, online simulations, and interactive apps showcased its rotation, light curves, and trajectory, helping people visualize a fragment from another star system passing silently through their skies. Scientists hoped these experiences would foster appreciation for the universe's vastness and the beauty of natural phenomena, highlighting curiosity and understanding over fear. The visitor's ephemeral nature reminded observers that cosmic encounters are fleeting and precious. Its short time in the inner solar system meant that every observation counted. Yet the absence of danger allowed careful study, patience, and collaboration to thrive. Scientists reflected on how fortunate humanity was to witness such a journey without any threat, turning a rare event into an enduring lesson about exploration, observation, and wonder. In laboratories, modeling its composition and motion continued. Researchers examined how variations in brightness corresponded to shape and surface properties, simulating conditions that had existed millions of years before the visitor entered the solar system. The lack of peril allowed these studies to be conducted methodically, providing deeper understanding of interstellar object physics while maintaining a sense of awe at the resilience and mystery of a distant traveler. Ultimately, the visitor became a symbol of cosmic perspective. It reinforced that the universe can inspire fascination without danger, that profound knowledge can be gained from silent observation, and that curiosity is a powerful driver of human inquiry. Scientists, educators, and the public alike were united by the shared recognition that the cosmos holds wonders that can transform understanding without ever posing a threat. Even as telescopes could no longer track it, the visitor's influence endured. Its images, data, and trajectory served as a permanent reminder that not all remarkable events carry danger. Some simply arrive to be observed, studied, and marveled at. In its quiet passage through the solar system, the visitor offered humanity a rare gift, a chance to feel small yet connected, to be witnesses to a journey that spanned light years, and to appreciate the quiet beauty of a universe that inspires wonder without harm. The interstellar visitor, with no threat and only the story it carried, became a testament to curiosity and the human desire to understand. Scientists remained captivated, continuing to analyze every piece of data it left behind. The encounter reinforced a simple truth: the universe can engage the mind and stir the imagination without ever needing to endanger the observer, and sometimes, the most profound experiences arise not from fear, but from unbounded wonder. The memory of the visitor lingered in classrooms, observatories, and minds worldwide. Its safe passage allowed everyone to focus on discovery, understanding, and appreciation. It reminded humanity that the universe offers lessons in physics, chemistry, and cosmic history, often arriving quietly and leaving an enduring imprint. In a world accustomed to reacting to crises, this event offered a rare, pure opportunity for curiosity, reflection, and awe. The interstellar visitor was more than a passing curiosity, it was a tangible connection to the broader galaxy. By studying its trajectory, scientists gained insights into how matter moves between stars, tracing patterns that extend far beyond the solar system. Its hyperbolic orbit, unbound by the Sun, demonstrated that objects can traverse immense distances while retaining structural integrity. Each measurement of its motion, no matter how subtle, contributed to a larger understanding of galactic dynamics, revealing how debris from distant systems might spread and interact over millions of years. Observing the visitor's shape and rotation provided clues about the conditions under which such objects form. Its elongated, tumbling structure suggested collisions or gradual erosion in interstellar space, processes that are difficult to study directly elsewhere. By analyzing these physical properties, scientists could infer the types of environments present in other star systems. In this way, a single object became a miniature laboratory, offering lessons on formation, resilience, and the evolution of small bodies across the galaxy. Composition studies revealed chemical fingerprints of distant worlds. Light curves, spectroscopic data, and infrared measurements allowed researchers to speculate about surface materials, ices, rocks, and possibly organic-rich compounds. Comparing these characteristics to objects in the solar system highlighted similarities and differences, helping refine theories of planetary formation. The visitor was effectively a sample from another star, allowing humanity to study alien chemistry without leaving Earth's neighborhood. By measuring subtle accelerations, astronomers learned how interstellar forces act on small bodies. Radiation pressure from nearby stars, sparse dust interactions, and minor outgassing all influenced its trajectory. Modeling these forces enhanced understanding of how interstellar objects evolve over time and how they interact with the galactic environment. These insights are vital for predicting the behavior of future interstellar visitors and for understanding the long-term evolution of material traveling between star systems. The visitor's journey illustrated the prevalence of interstellar debris. Its existence suggested that countless fragments are likely drifting invisibly through the galaxy. Many of these bodies could one day pass through other systems, potentially delivering chemical compounds or even acting as seeds for complex processes elsewhere. By studying one object in detail, scientists could begin estimating population density, size distributions, and the likelihood of encounters in different regions of the galaxy. Its elongated structure provided an opportunity to test physical models of interstellar survival. Objects traveling for millions of years must withstand collisions, cosmic radiation, and extreme temperatures. Observing how this visitor maintained its coherence helped scientists refine models of small body mechanics and material strength in environments vastly different from the solar system. These lessons extend beyond one object, offering insight into the durability and behavior of material across the Milky Way. The visitor also helped calibrate observational techniques. Tracking such a faint, fast-moving object required precise coordination among telescopes, both on Earth and in space. Scientists used this event to test imaging, spectroscopy, and data-sharing protocols. Lessons learned from observation efficiency, noise reduction, and cross-validation of data will improve future detection of interstellar objects, ensuring that researchers can maximize scientific returns when new visitors appear. Studying the visitor's light curves enabled scientists to reconstruct rotation patterns, which in turn provided clues about internal density and surface properties. This method allowed a detailed study of an object too distant to resolve visually, demonstrating how indirect measurements can reveal the hidden structure of bodies beyond our solar system. Applying these techniques broadly could illuminate the diversity of interstellar objects and the physical principles governing them. The visitor offered insights into the movement of matter on galactic scales. Its trajectory, combined with galactic velocity maps, allowed astronomers to speculate about its likely origin and the relative motion of stars in its neighborhood. Tracing its path backward provided hints about how interstellar objects might travel through star clusters, spiral arms, or even interstellar voids, connecting local observations with the broader architecture of the Milky Way. Infrared observations revealed thermal properties that suggested surface heterogeneity. Differences in heat retention and emission patterns allowed scientists to model the distribution of materials across its surface. These insights help understand how cosmic objects adapt to changing environments, highlighting the effects of long-term exposure to interstellar radiation and the minimal but persistent influence of galactic forces. The visitor also taught lessons about chemical preservation. Despite traveling for millions of years, it retained materials capable of reflecting and scattering light in distinctive ways. These chemical fingerprints are crucial for understanding how matter survives interstellar transit, providing context for theories of panspermia and the distribution of organic compounds throughout the galaxy. Each measurement hinted at the chemical resilience of small bodies over cosmic timescales. By combining observations from multiple observatories, scientists could construct a multi-perspective model of the object. This triangulation offered insights into its three-dimensional shape, rotational axis, and tumbling dynamics. Applying these methods to other interstellar objects will allow astronomers to build a more complete picture of how such travelers behave across the galaxy, bridging the gap between single-point observations and holistic understanding. Its fleeting visibility underscored the importance of continuous monitoring. The visitor's brief passage demonstrated that interstellar encounters can be sudden and unpredictable. By analyzing the data collected during its transit, scientists refined strategies for early detection and rapid response observation, which are critical for maximizing scientific yield from such rare events. The galaxy is vast, but its secrets can be glimpsed with careful preparation and vigilance. Spectroscopy revealed subtle differences between the visitor and solar system comets or asteroids. These differences provided evidence of diverse chemical pathways and formation conditions beyond our neighborhood. Comparing these properties to local analogues allowed researchers to hypothesize about temperature, pressure, and radiation conditions in other stellar nurseries, giving a broader view of galactic chemistry. The visitor's hyperbolic path illustrated gravitational interactions beyond the Sun. By studying deviations in trajectory, scientists inferred the influences of galactic tides, passing stars, and interstellar medium drag. These observations help model the motion of interstellar bodies across the Milky Way, connecting the behavior of individual fragments to the dynamics of entire stellar populations. Rotation and tumbling measurements offered insight into collisional history. Irregular spin suggested past impacts or tidal disruptions, which could inform models of interstellar debris evolution. Understanding these processes helps scientists predict the structural diversity of future visitors and provides a framework for interpreting their physical characteristics without direct sampling. Dust ejection events, though minimal, were carefully analyzed. Small fragments or transient emissions offered clues about surface composition and interactions with sunlight. Observing these phenomena in an interstellar context helped scientists distinguish between local solar system effects and processes likely occurring in other star systems, extending our understanding of how matter behaves under varied cosmic conditions. The visitor helped refine size and mass estimation techniques. Its faintness and rapid motion presented a challenge, but careful observation across multiple instruments allowed for accurate modeling. These methods will be invaluable for studying smaller or more distant interstellar objects, expanding our ability to map and understand the hidden population of matter moving through the galaxy. Even minor variations in brightness provided valuable data. Patterns of reflection, shadowing, and scattering informed models of surface roughness and internal density. Applying these analyses to other interstellar objects will improve predictions of rotation, structural integrity, and potential hazards or scientific interest for any future encounters. The visitor's presence emphasized the interconnectedness of the galaxy. Objects that drift between stars carry with them chemical signatures, formation histories, and dynamics of their home systems. By studying them, scientists can piece together a mosaic of galactic evolution, learning how material circulates, how stars interact, and how diverse environments produce the array of small bodies observed today. The opportunity also highlighted the importance of archival data. Observatories revisited prior surveys and images, uncovering traces of the visitor before its official discovery. This retrospective analysis demonstrated that the galaxy continuously offers information if we are attentive, allowing scientists to expand knowledge of interstellar populations by mining existing data and connecting observations across time and space. The visitor's journey provided a template for future exploration. It established benchmarks for observational methods, data sharing, and collaborative analysis. By studying a single interstellar object in depth, scientists gained tools and experience that will make subsequent encounters even more informative, gradually building a growing understanding of the galaxy's content, motion, and diversity. The presence of a foreign object encouraged international cooperation. Observatories from different continents coordinated observations, contributing to a richer dataset than any single nation could achieve. This collaboration modeled how the study of the galaxy requires collective effort, where the insights from one region or telescope can complement and enhance those from another, creating a global understanding of interstellar phenomena. Finally, the visitor reminded humanity of perspective. Its passage showed that our solar system is a small part of a vast, dynamic galaxy filled with wandering material. Studying it offered lessons about origin, motion, and the diversity of star systems. Every measurement, spectrum, and image helped transform a faint point of light into a source of knowledge about the broader Milky Way, turning fleeting observation into lasting insight about our place in the cosmos. Even after it vanished from view, the visitor's impact on galactic science endured. Data collected during its transit informed models of interstellar matter, dynamics, and chemistry. Its journey underscored the value of careful observation, patient analysis, and global collaboration. By studying this single object, scientists gained a richer understanding of the galaxy itself, a reminder that even brief cosmic encounters can illuminate the grand story of the universe. As the interstellar visitor continued its journey away from the Sun, it left behind more than fleeting images and data points. It left quiet gifts in the form of knowledge, inspiration, and perspective. Its passage had been brief, almost imperceptible against the vast backdrop of the cosmos, yet it provided humanity with a tangible connection to worlds far beyond the solar system. Each measurement, spectrum, and observation became a small treasure, a fragment of insight gifted to those who had looked closely enough to see. One of the most profound gifts was a deeper understanding of interstellar travel. Scientists could trace the visitor's path, calculating its hyperbolic trajectory and estimating the immense distances it had traversed over millions of years. This journey reminded humanity that the galaxy is filled with travelers, silent witnesses to the evolution of stars and planets far from our own system. The object's endurance and survival offered clues about the resilience of matter drifting through the emptiness of interstellar space. Its unusual elongated shape, revealed through careful photometric and spectroscopic study, provided a unique window into the processes shaping small bodies outside the solar system. Unlike the more familiar spherical or irregular comets of the Sun's neighborhood, this object had likely been sculpted by collisions, rotational stress, or erosive forces over eons. By studying its form, scientists gained insight into mechanical properties, surface evolution, and long-term survival of interstellar material. The visitor's subtle accelerations offered lessons in physics rarely observed so directly. Deviations from a purely gravitational path, likely caused by sunlight pressure or minor outgassing, allowed researchers to test models of non-gravitational forces acting on small bodies in space. These insights help refine predictive models for future interstellar objects, ensuring that subsequent encounters can be analyzed with greater accuracy and understanding. Spectroscopic studies revealed faint but meaningful chemical signatures. Light reflected from the surface suggested the presence of rock, ice, and possibly organic-rich compounds. These signatures, even in their subtlety, hinted at the diversity of chemistry present in distant planetary systems. By comparing these findings to solar system objects, scientists gained a rare glimpse of the materials that compose the galaxy's wandering debris. Photographs and measurements collected from multiple observatories created a mosaic of information. Each image captured a different perspective, a slightly altered angle, or a different wavelength. Combined, these fragments painted a picture of rotation, shape, and surface variation, allowing researchers to reconstruct the object's properties without ever touching it. The collaborative nature of this effort itself became a quiet gift, illustrating the power of shared scientific endeavor. The visitor's brief passage encouraged the development of observational techniques. Its rapid motion and faint glow posed challenges that tested instrumentation, software, and coordination. Scientists refined their methods in real time, learning how to detect, track, and analyze interstellar objects effectively. These improvements will be invaluable for future encounters, ensuring that humanity is better prepared to study the fleeting messengers drifting through the galaxy. Even amateur astronomers played a role in this discovery, submitting observations that contributed to the global dataset. Their participation was a reminder that exploration is not confined to professionals. The universe offers opportunities for anyone with curiosity, dedication, and the ability to look closely. This democratization of discovery enriched the scientific record and encouraged broader engagement with space exploration. The visitors' light curves revealed rotation patterns, offering clues to internal density and surface irregularities. By analyzing periodic variations in brightness, scientists inferred that the object was tumbling rather than spinning smoothly. This tumbling provided insight into past collisions or tidal forces it had experienced during its interstellar journey, revealing a history written in light rather than stone. Thermal measurements added another layer of understanding. Variations in infrared emission indicated surface heterogeneity and provided estimates of albedo and thermal inertia. These data allowed researchers to simulate the object's response to solar radiation, deepening understanding of how interstellar bodies survive and evolve in environments far different from their points of origin. The visitor's existence also encouraged reflection on the prevalence of interstellar material. Its presence demonstrated that fragments from other star systems pass through the solar system more frequently than previously appreciated. Each such object, though fleeting, carries chemical, physical, and dynamical information about environments far from Earth, suggesting that the galaxy is filled with messengers waiting to be observed. By comparing this object to solar system comets and asteroids, scientists could identify both similarities and differences, enhancing knowledge of planetary system formation. These comparisons revealed that some processes, like erosion and rotational stress, are universal, while others, such as chemical composition and surface coloration, reflect the unique conditions of distant stellar neighborhoods. The visitor's trajectory illuminated the motion of matter on galactic scales. Its path, combined with galactic velocity maps, suggested regions it may have traversed and even potential star systems of origin. This information provided a rare empirical anchor for understanding how debris migrates across the Milky Way, bridging observational astronomy with models of stellar kinematics. Its endurance offered lessons about material survival in interstellar space. Despite traveling for millions of years, the object remained intact, resisting fragmentation and erosion. This resilience informs theories of small body longevity, suggesting that some fragments can endure cosmic forces over extraordinary timescales while retaining enough integrity to provide scientifically meaningful information. Dust emissions, though minimal, provided clues about surface composition and interaction with solar radiation. Observing these faint ejections allowed scientists to confirm that outgassing was responsible for minor accelerations, demonstrating the subtle ways in which physical forces act on bodies far from their home systems. These phenomena offered a quiet but powerful confirmation of theoretical models. Light scattering patterns offered insights into surface texture and reflectivity. Variations in brightness and shadowing helped reconstruct surface features at scales unresolvable by direct imaging. This indirect method of analysis illustrated the creativity and ingenuity required to study objects so distant and faint, transforming faint glimmers of light into detailed scientific knowledge. The visitor inspired international collaboration on an unprecedented scale. Observatories across continents coordinated to track its motion, share data, and refine models. This cooperative effort exemplified the global nature of astronomical science and demonstrated how humanity's shared curiosity can transcend borders, turning a passing object into a unifying scientific experience. Even educational outreach benefited from its passage. Students and the public could explore simulations of its path, rotation, and light curves, engaging with real scientific data. The visitor became a tool for teaching orbital mechanics, observational astronomy, and the physics of small bodies, inspiring curiosity in a new generation of learners who might one day study the next interstellar messenger. The visitor also highlighted the value of archival data. By searching older images and surveys, scientists could extend observations before its official discovery, providing additional information about its path and brightness. This retrospective study underscored that the galaxy continually offers opportunities for discovery, and careful attention to existing records can yield insights even after the moment has passed. Its interstellar origin reminded humanity of its small but connected place in the Milky Way. The object's journey linked distant star systems to Earth in a tangible, observable way, emphasizing the continuity and interconnectedness of cosmic processes. Observing its passage fostered a sense of perspective, reminding us that the universe is vast, dynamic, and full of surprises waiting to be understood. Researchers continued modeling its internal structure based on rotation and light curve data. Even after it faded from view, these models provided insight into density, cohesion, and material distribution. Each analytical layer added to the scientific understanding of how such objects survive interstellar transit, revealing lessons that might apply to countless other fragments drifting silently through the galaxy. Its quiet, uneventful passage reinforced the principle that discovery does not require danger. The object posed no threat, yet its presence delivered profound knowledge and inspiration. This encounter demonstrated that the most valuable cosmic events are not necessarily cataclysmic, they can be subtle, fleeting, and entirely benign while still offering immense scientific and philosophical significance. The visitor's final gift was perspective. Its fleeting journey through the solar system reminded humanity of the immense scale of the galaxy, the diversity of stellar systems, and the endurance of matter traveling across light years. Observers were humbled, inspired, and educated simultaneously, receiving a lesson in patience, observation, and the quiet, persistent beauty of the cosmos. Even in absence, its legacy persisted. Data, images, and models allowed continued analysis, revealing new insights long after direct observation ended. The visitor had departed physically, but its contributions to science, education, and imagination would endure indefinitely, leaving behind a record of wonder, collaboration, and discovery that would guide humanity's gaze toward the stars for years to come. Ultimately, the visitor became a symbol of cosmic connection. Its passage showed that the universe offers lessons, insights, and inspiration without requiring peril or drama. Each measurement, spectrum, and observation became a lasting gift, a fragment of knowledge linking Earth to distant star systems, reminding us that even the smallest, most ephemeral travelers can leave profound impacts on our understanding of the galaxy. Through its journey, humanity received not just data, but a renewed sense of curiosity and perspective. The visitor's silent drift offered time for reflection, study, and imagination. It left no explosive mark, no threat, but countless subtle traces, the gift of knowledge, the joy of discovery, and the reminder that the galaxy is full of mysteries waiting patiently for those who are willing to observe, ponder, and marvel. The interstellar visitor, drifting onward into the infinite expanse, became a messenger not of alarm but of enlightenment. Its passage reaffirmed the value of patience, collaboration, and careful observation. In leaving behind these quiet gifts, it transformed a fleeting encounter into a lasting legacy, offering humanity an enduring connection to the broader universe and a gentle lesson in the beauty and wonder of cosmic exploration.